Okay, that should make it work. Good. Okay. So, sorry for this delay. Okay, I think now we are live, so we are ready to go. Let me just share my slides. Okay. So, hello everyone, and welcome to the ICCV 2021 tutorial on large-scale visual localization. So this tutorial is a follow-up of previous editions that were organized in previous ICCV, ECCV, and CVPR conferences with topics on large-scale visual place recognition and image-based localization. So today's schedule includes presentations by Yanis from Athena Research Center, Eric from Niantic, Sudipta from Microsoft, and then Zuzana, Torsten, and myself from CTU in Prague. Okay, so the schedule is split in three parts. First, we start with image retrieval for coarse localization covered by Yanis and myself. We'll go through more, starting from basics of visual representation and how to deal with coarse localization in the form of place recognition as image retrieval, and Yanis will cover some special flavors of metric learning, such as knowledge transfer, data augmentation, and attention. Then in the second part, by Sudipta, Torsten, and Zuzana, it's about more precise visual localization, which will include talks about camera pose estimation, feature-based visual localization, and then again a special flavor of privacy preservation in a localization approach. And finally, in the last part, Eric will talk about learning-based visual localization. After the tutorial, we will make the slides and the recording of this tutorial publicly available. And don't forget that if you have any questions, you should make these questions through the YouTube chat. So if there is time during the presentations, we will try to on the fly or at the end of the talk reply to these, or even in the chat after each talk has finished. Okay, so we should go on, and we will be starting with the part that I will be presenting. 1 second to share my screen again. Okay. So in the first part of this tutorial, we will talk about coarse localization in the form of place recognition and how to deal with that as instance search, as image retrieval, like where we perform instance level matching between images. I will go through handcrafted approaches, but also learning-based methods, and then talk about similarities between these two different cases. Okay. So in place recognition, we're given a test image, and the goal is to predict either the GPS coordinates of the location where this test image was taken, or to predict the landmarks or places that are shown in the image among a large list of known places. So it should be clear that the task is dealing with a huge number of classes, for instance, all named locations or known landmarks, or each distinct spot in the space of GPS coordinates. And moreover, the intra-class variability is relatively small. Variations mostly originate from viewpoint, illumination changes, and other than that, the inter-class similarity is also high. So in general, it becomes hard to train an n-way classifier in this case, but as we will see later, this might not even be the best solution. So these aspects make the task close to instance search. And what we need is to identify the most similar items from a large collection of reference examples. Once these are identified, then recognition or localization are performed with nearest neighbor classifiers, kernel density estimation, or other approaches. The standard setup is that we're given a large collection of images, okay, with known location, and then given a test image, we need to compute the pairwise visual similarity between this image and all the database images. Efficiency in the estimation is crucial due to the large database size. Okay, so after computing the similarity of the query to all the database images, then we need to rank them according to this similarity, and in the end exploit only the top ranked ones. In the simplest form, we assign the location of the most similar image. So as mentioned earlier, someone can do further processing to improve this prediction, but we will not cover this processing in this tutorial. We will mainly be focusing on how to estimate this pairwise visual similarity. So to provide the appropriate context, I will briefly go through some of the relevant benchmarks for the task of place recognition. First, we have datasets whose database is collected from Google Street View or from Flickr, and each image in the database is geotagged, while test images are often mobile photos taken at the same cities. Some of the challenges included are environmental changes and different illumination conditions, such as one needs to match day images with night images. Then we have instance retrieval benchmarks on the domain of landmarks and buildings, where the ground truth is, in this case, created manually. So in 2018, we revisited the popular Oxford and Paris benchmarks and standardized a challenging distractor set of 1 million images. Some of the challenges here are extreme viewpoint changes and small objects with severe background clutter. Then we have datasets that originate from Kaggle competitions organized by Google. The Google Landmarks dataset is used for recognition and retrieval at large scale with more than 200,000 unique landmarks. So the images are collected from Wikimedia Commons, and there's no guarantee that actually all the images inside the class depict the same views of the object. So many classes are rather noisy, and this forms a main challenge to perform training using this dataset. So now the approaches that I'm including in this tutorial come mainly from two families. First, the case of global image descriptors, and second, the case of voting approaches with local descriptors. In the first case, the descriptor extraction process takes as input an image and maps it to a point in a high-dimensional space. So the benefit of such a representation is that it makes instance search reduce down to similarity search in high-dimensional spaces, and there is compatibility with efficient k-nearest neighbor search. Now, a different case is when an image is represented by a set of local descriptors. The feature extraction process takes an image as an input and then provides a set of d-dimensional vectors. And now the image similarity is in the form of a pairwise similarity function that takes as input two such sets of high-dimensional descriptors and estimates the scalar similarity value. So in this family of approaches, local descriptors need to be stored and indexed separately. So in that case, when we're dealing with local descriptor sets, a common similarity measure is the one that is obtained with a matched kernel, which is also what I will be calling a voting approach. So image similarity in that case is proportional to sum in all the similarities from all pairs of local descriptors between the two sets. So for these individual similarities, we are using a kernel function S, which I will be calling local similarity function, and which acts on embeddings of the initial descriptors. So these embeddings with embedding function G, as shown here, aim to project local descriptors to a more discriminative space. And I'm here saying that similarity is proportional to this quantity mainly because I'm skipping any normalization factor, just for simplicity. Now, there is a case where these two families, where these two methods are actually equivalent. And this is when the local similarity function is a linear one. It is a dot product. So, and here is how the voting approach looks like in that case. Then, due to the linearity of the operations in this formulation, we can instead sum aggregate the local descriptors or their embeddings in advance. So, and this is what results in the global descriptor. And now similarity of global descriptors with a dot product actually gives the result that is identical to the voting approach without having to enumerate all the possible votes. So it often happens that we have to go with one way or the other depending on the configuration of and the parameterization of our model. So if the local similarity function would be nonlinear, then we typically have to stay with the voting approach. So in the rest of the tutorial, I will talk both about voting approaches and global descriptors, and we'll discuss the benefits of each. As said, the voting approaches act on local descriptor sets. In practice, also all descriptors or the global descriptors that I will talk about take as input such a set of local descriptors. So we start from a local descriptor set, optionally use discriminative higher dimensional embeddings, and then aggregate to construct a global descriptor. Finally, this is post-processed in ways that improve instances. And all these parts that are shown here can be handcrafted or learned. So I first start from classical, older, handcrafted approaches. So why does it make sense to still talk about handcrafted approaches here? From one point of view, historical reasons. Second, because handcrafted approaches are often modified so that either parts of them are learnable or they're fully learnable in end-to-end manner. And even actually without end-to-end learning, some handcrafted approaches are still very relevant and top performing for the task of location recognition. And this is in contrast to many other computer vision tasks. And this is also a similar case in some parts of the second part of this tutorial, which is about precise camera pose estimation. So handcrafted approaches are still good and relevant for visual localization, and the task is not necessarily fully dominated by deep learning approaches. So this is the part where maybe in other tasks someone would say once upon a time, but I said, okay, this is not the case in the task of localization. So we still, often in order to be invariant to geometric transformations and robust to background clutter, we often rely on a local feature detector and local descriptors. So a set of key points are detected and a local descriptor extracted from each. And this is how we obtain a set of local descriptors to represent an image, while nowadays, of course, some parts of this pipeline are replaced with their learnable counterparts. Now, the linear model that I mentioned before matches every single local feature of one image with each of the local features of the other. And now I'll move to probably the most popular matching approach, which is based on the bag of words model. So the space of local descriptors is quantized. A clustering algorithm is used to form what is called the visual codebook, where each cluster represents a visual word. And then matching of local descriptors is only performed within the same cluster, the same visual word. And not all pairs, not pairs across different clusters contribute to the image similarity. And if now we see this as a voting approach, and we want not all pairs to contribute the similarity so that we don't have to enumerate them all, there is actually an embedding function, a simple embedding function that allows us to do that. So this embedding in this case has size equal to the codebook size. And the only non-zero component is the one that corresponds to the visual word that this local descriptor is assigned to. And in this way, there is a clear equivalence between the voting approach and the global descriptor in the case of the bag of words model. So the voting approach will enumerate all the votes between all descriptors of two images that fall in the same visual word, while the global descriptor will end up with a so-called bag of words histogram. So aggregating these binary embeddings is equivalent to accumulating occurrences per visual word. Now the Vlad descriptor instead, which is an extension of the bag of words, accumulates a whole vector instead of the count. So, and this vector is the residual vector, which is the one that points from the corresponding centroid to the descriptor itself. So we can see now that this embedding that we're using, okay, maps a local descriptor to a more discriminative, much higher dimensional space. This ends up in a global descriptor with much higher dimensionality than bag of words, while, however, in practice, dimensionality is typically reduced with PCA without significant loss of performance to some extent. And this means that actually there's no reason to consider Vlad in the case of to see it as a voting approach. However, if we do that, okay, if we now see Vlad as a voting approach, it should be clear that the votes that are accumulated now are much more fine-grained than the case of bag of words. So bag of words was accumulating a single vote in this case, and now we have a fine-grained similarity, a vote that is actually a dot product between residual vectors. So a benefit of Vlad is that the dimensionality of the final descriptor and the complexity of the matching does not depend on the number of input local descriptors. And a number of methods in the literature have used, take advantage of this property and have used, for instance, densely sampled features instead of local features to exploit this. For instance, that's the case with dense shift. And in the case of Vlad and the work of Tori et al., this is known as dense Vlad. We normally prefer to, when we're dealing with Vlad-like approaches for global descriptors, typically a meaningful configuration uses a small codebook. Now, what happens if the codebook size is significantly larger? And actually, in practice, bag of words, to be discriminative enough, needs a much larger codebook. So in that case, a global descriptor is very sparse and is not meaningful. What we need in that case is to see it as a voting approach and use inverted files that provide an efficient way to enumerate all the votes. So for each visual word now, we keep a list of features that are assigned to it for every image in the database. Then a test image comes, and what we need to do is only to visit the lists for the visual words that appear in each set of local descriptors in the query image. Now, each list in the inverted file needs to store only how many descriptors of each database image are assigned to the corresponding visual word so that we can accumulate the appropriate amount of votes. And this is how to deal with bug of words and very large code books, and still enjoy efficiency of the search. Now, a more fine-grained voting compared to this approach is performed by an extended version, which is the aggregated selective match kernel. In that case, we keep one representative vector per visual word for each image that this word appears in. And this vector is the sum of residual vectors, where residuals are as in the case of Vlad, and this vector is consequently L2 normalized. Now, for estimating the image-to-image similarity, what we need to do is that we go over common visual words between two images. And for each one, we estimate the corresponding vote by again a local similarity function that what it does, it discards the negative votes and uses a monomial kernel to balance the strength between strong and weak votes. And now, due to this nonlinearity, there is no equivalence of this voting approach to a global descriptor. But it is actually this nonlinearity which makes it work noticeably better. So efficiency, again, is achieved once more with inverted files, because ASMK is directly compatible with that because of the use of descriptor quantization and the visual code. Now, the aggregation that is performed per visual word in ASMK is actually a way to somehow handle bursty features that tend to correspond to repeating structures and also tend to cause undesirable effects of overcounting the votes. So in ASMK, repeating structures tend to be assigned to the same visual word, and a single descriptor will be kept, and at most a single vote will be accumulated during the matching, and this is what somehow handles the burstiness effects. Now, one of the benefits of voting approaches that individually index the local features with, for instance, an inverted file is the possibility to form point-to-point correspondences during this voting procedure. And such tentative correspondences are the input to ransack-like special verification. So, and then we obtain the number of inliers, which is a measure that one can even a bit intuitively threshold to verify if there is a true match or not between two images. And this is often an essential step as a re-ranking step and verification in place and landmark recognition. So at this point, I'm done, let's say, covering some of the relevant handcrafted, more classical approaches, or at least approaches that appeared in the literature during the era that we were mostly relying or only relying to handcrafted descriptors. And now I'll move to the more recent learning-based methods. So here, it's good to see the obvious similarity to what was presented before, that again, with CNNs, what we obtain is a global descriptor as a processing and aggregation of a local descriptor set. Now, this local descriptor set is obtained, for instance, with a fully convolutional network. We feed an image, and the output 3D tensor of activations is seen as a dense set of local descriptors. The depth is equal to the dimensionality of the descriptor. And in all the descriptors that I will describe in the following, this local descriptor set, this 3D tensor of activations, is actually considered as their input. So inspired by classical approaches, in the work of Mohedano et al., they use this dense set of deep local descriptors to first learn a visual codebook and then use the bag of words approach. In their work, this is used with networks that are pre-trained on ImageNet. And bag of words performs actually, in that case, hard assignment of one descriptor, each descriptor to one visual word, which is not appropriate for end-to-end training, where soft assignment would be actually the way to go, which is actually what is done in the NetVLAD approach. So NetVLAD modifies VLAD to use an embedding with soft assignment over all visual words. Now the residual is calculated not only for the closest visual word, but for all of them, and the residuals are weighted according to the distance from the corresponding reference point. In an end-to-end manner, both the centroids are learnable parameters, and the same holds for the whole fully convolutional network that is trained to produce better input local descriptors for blood. As before, we produce a high-dimensional global descriptor that is consequently reduced with PCA. Now, it's good to see what the discriminative power of these CNN activations allow us to do. Okay, we are given now the chance to produce a global descriptor even without any high-dimensional embedding in the loop, as the ones that are involved in blood. So, for instance, without any embedding function, simple sum pooling of the local descriptors is used by Spock descriptor. And now when we compare the two global descriptors, simple dot product, actually this is equivalent to the voting approach that cross-matches all the feature pairs and accumulates the votes. And this is what is done implicitly to compare two images. What is interesting here is that a global descriptor like that, if estimated with a handcrafted local descriptor such as Shift, performs quite poorly. But now this is possible because of the high discriminative power of the CNN activations. An improvement of Spock uses weighted sum pooling. First, each channel is weighted in an IDF-like manner, which means the channels that fire a lot are down-weighted. But what I'm mainly focusing on is the saliency map that is produced based on the L2 norm of each of the local descriptors, which is then used as a weight in the weighted aggregation. There are actually more descriptors in the literature that use attention maps. So Kim et al. Introduced a set of layers that take as input the 3D tensor of activations and produce a saliency map. So the value at each location forms a weight for the local descriptor, and this is used for the weighted aggregation to obtain the global descriptor. Now, equivalently, what is interesting is that if we see this as a voting approach, then we can see how the votes that were accumulating are actually down-weighted according to these weights of the attention map. If instead we use max pooling instead of sum pooling, there is no equivalence to a voting approach. But still, this approach has a different interpretation. So we now do not see the 3D tensor of activation as a set of dense local descriptors, but we rather see it as a set of 2D heat maps of activations. And for each feature map, we keep the maximum activation and store it in a vector. So this is a much more localized descriptor where each descriptor component corresponds to an image region. When computing the pairwise image similarity with descriptor dot product between two MAC descriptors, we implicitly form correspondences, in particular one correspondence per component. So these are region correspondences. So therefore, matching MAC descriptors operates implicitly as a one-to-one matching scheme, while the ones with sum pooling operate as a many-to-many matching scheme, since they're equivalent to a voting approach that cross-matches everything. Now, a generalization of the previous cases is given by the generalized mean pooling. So for each local descriptor now, we compute the component-wise power of P, average all descriptors, and then raise again to the component-wise power of 1 over P. So it's clear if we see here that if you set P equals to 1, this is equivalent to sum pooling and the Spock descriptor. While P tends to infinitive, the descriptor tends to MAC and max pooling. We can see the effect of the power of P of the P hyperparameter on each of the 2D feature map activations, where low P seems to have spread attention around several regions, or while larger P is much more localized. So small P in some extent captures textures, while larger P localizes details. So parameter P can be either hand-tuned or learned. Now a more hybrid case is RMAC, which combines max and sum pooling. So what we have here is uniformly sampled regions at different scales, compute MAC from each region, L to normalize it, and then sum aggregate. Now if we have a look at some quantitative results, we're evaluating here at large scale retrieval features that are obtained from a network that is pre-trained on ImageNet. So what we see here is that some pooling performs the worst, while the hybrid RMAC is the best in this case. And even though I have not talked about any training fine-tuning of the backbone yet, here we can see that significant improvements are achieved after fine-tuning the target for the target tasks. So in our experiments, we have seen that GEM is the best performing after fine-tuning. So here is a brief look at an approach that was presented at the main conference, ICCV 2021. It's the DOLG descriptor. So it is a different way of aggregating these local descriptors into a global one. So while it includes a learnable part to do that. So right after the backbone, there is a standard branch to generate a global descriptor, while in parallel, the 3D tensor of activations, it is processed with multiple address convolutions and with self-attention. And now the fusion module, what it does is that it computes the part of each local descriptor that is orthogonal to the global descriptor. And then it uses this in the aggregation along with the global descriptor. So in some sense, this pronounces the differences from the global descriptor. So according to the results in the paper, DOLG is currently a top-performing global descriptor for instance search. So it seems that the popular approach is with CNNs is to train global descriptors. They're easy to train. We have image level labels, global label that are easier to obtain. And additionally, the global descriptor is compact and efficient in search. On the other hand, local descriptors better handle occlusion and clutter. So I will now present a more principled way to how to learn local descriptors while the supervision only comes from global labels. So we know whether two images show the same object or not. The starting point is metric learning of global image descriptors. So the 3D tensor of activations, as we said, is pulled into a global descriptor, and now global descriptors of matching images are pushed closer, while descriptors of non-matching images are pushed apart. Now let's take a look at global sampling, the Spock descriptor. As discussed earlier, global descriptor similarity can be decomposed into aggregation of many similarities of local descriptors, all the possible combinations. So therefore, while we optimize a global descriptor, implicitly, indirectly, we optimize the local descriptors too. And as a consequence, we improve global descriptors, but local descriptors as well. Now, this simplistic architecture is extended to amplify the training of local descriptors and to improve also the synergy with the ASMK approach that I described earlier. A fully convolutional network is used to obtain, as before, as always, the dense set of local descriptors. And first, what we do is that we perform local smoothing with 3x3 average pooling, which improves the aggregation that is performed by SMK. Then we add a dimensionality reduction layer with a 1x1 convolution. And the important detail here is that this is initialized with a closed form solution, which is actually the result to perform whitening of the descriptor space and to provide more discriminative local descriptors. Then we add a non-parametric attention function. So the importance now of each local descriptor is simply equivalent to its L2 norm. This is the same as was used in the crowd descriptor that was shown earlier. Then the obtained attention map is used to perform weighted sampling of the dense local descriptor set. So now, during inference of these, as we call them, how local descriptors, is performed in a slightly different way. First, the local smoothing and dimensionality reduction and attention are applied in the same way as in the training. But now the attention scores are used to select the strongest local features. So the attention map there acts as a local feature detector. And therefore we can choose the corresponding local descriptors. So now local descriptors with low attention score are the ones that are skipped and are also the ones that contribute the least in the cross-matching and the final similarity. So this is the local descriptors set that we will use to represent an image and to perform the matching with ASMK. Here is an example of the input image and the attention map before and after training on landmarks. So the attention improves significantly by focusing on objects that are relevant to the training domain and avoids also background and informative regions. So this process is performed at multiple different resolutions, and the strongest features across all resolutions are selected. So in the case of ASMK now, we're going back to the way that the image similarity is computed, and there is implicitly a many-to-many matching scheme within one particular visual word. All features of that visual word from one image are matching to all features of the same visual word from another image. However, as we said before, only a single vote is taken into account, and that's the useful thing to avoid overcounting. Now, the more features that are aggregated in the same visual word, the smaller the memory footprint is for ASMK. And aggregated features are typically from repeated structures or nearby locations due to the large receptive field that the FCN has. And that's also an aspect where the 3x3 local smoothing that I described before tends to help. So in contrast now to other deep local feature detectors and descriptors where they target precise feature localization because the target task is image registration, we do not perform any process such as non-maximal suppression, and we do not follow such a process. So in this case, these repeating patterns are aggregated into a single but improved representation, and that's beneficial. And this is happening without increasing the final memory footprint. So what is interesting here is that during training, we're optimizing a global descriptor. And then during inference, we slightly modify the architecture and use the network in a different way. But what happens is that we obtain better results. So this is actually different than many other cases where any discrepancy between training and inference results in performance drop. So the how local descriptors that I just described are inspired by DELF, which is an earlier approach, and this is actually our starting point. So DELF instead uses a full convolutional learnable block that in order to generate the saliency scores. In our experiments, we saw that the non-parametric one actually performs better, assuming that it overfits less. So, and in the original DELF paper, the network is trained with a classification loss, but actually switching to a metric learning setup is more than just a different loss. It's an essential detail, as it is the one that supports the interpretation of cross-matching local descriptors between two images. So here I'm showing the trade-off between performance and memory for instance search at large scale. So performance on the vertical axis, memory footprint on the horizontal axis. So what we can briefly see is that global descriptors perform poorly compared to how local descriptors indexed with ASMK, while how local descriptors perform better than the previously existing DELF. And at the same time, it performs roughly the same for significantly less memory. And something else that we can observe is that we achieve good enough results, even with small backbones such as ResNet 18, while other approaches typically rely on larger networks. So here is another example of a work at the main conference, the earlier days. It was presented as a method that improves the detection of how by using multiple attention maps and then jointly selecting the strongest features among all feature maps, among all attention maps. So attention maps are obtained by convolving the feature map with an indicator vector, which is the result of a transformation of the corresponding global descriptor. So many such transformations are learned, and the key ingredient is to enforce diversity between the multiple attention maps. So we have diversity of different detectors used. Here, a brief mention to another earlier work by a team at Google. It is often the case that in some recognition, place recognition approach, we are using both global and local descriptors, which in many cases come from a different model. While in this work, there is a standard branch for the global descriptor with a classification loss, and then attention with weighted sum pooling, as in DELF, with another classification loss. So, and therefore generating and optimizing both global and local descriptors in this process. Once more, a recent paper from the main conference. Now here we are assuming that local features and descriptors are given. And as mentioned earlier, they are commonly used for special verification and re-ranking states to improve retrieval results. So this method here is actually doing this in a learnable way. So local features of both images are given as input to a transformer that performs cross-attention between the two sets of features, while their position is also encoded with the standard position embeddings used in transformers. So this is what I would call learning how to match two sets of local descriptors, and actually fits well with the context and the things that are earlier presented in this talk. As maybe a minor weakness is that this function, as it is designed, is not symmetric, meaning if you swap the two images, the result is not the same, while the symmetry is a desirable property. So I mentioned previously in some parts like the corresponding losses that are used, but now I'll go again back to that. So typically in instance search and location recognition, we train a global descriptor. So image is fed to a network, global descriptor is obtained, and then we feed it to an appropriate loss, and we'll see now what these losses can be. So first option is a classification loss right after the global descriptor. For instance, standard choice is to have a softmax classifier with cross entropy loss. But actually a loss borrowed from another instance level recognition task, that of face recognition, is shown to perform really good for place recognition as well. So this is arcface, which what it does, it directly maximizes the decision boundaries in the angular space. So the problem here with classification losses is that it's not easy to obtain instance level labels for classification. And when having labels at different level, so at cursor level, for instance, for a whole landmark, not all within class samples depict the same view. And therefore, I expect this not to be as useful for instance search. While the situation somehow improves with subcenter arcface loss, which uses multiple centers per class to cope with these large intra-class variants. Now, what is closer to instance search is the losses that are used for metric learning. In this case, we need training data in the form of pairs. We need matching pairs and non-matching pairs. Popular cases are contrastive and triplet loss. Descriptors of matching pairs are pushed close, while of non-matching, they're pushed apart. And there's plenty of work about how to sample these pairs in the literature. But before I go to that, to talk about selection from the point of view of instance level recognition, I will talk about recent and improved loss. So because the previous ones, the ones for metric learning, they're hand designed to well align with the objectives of the target task. Now, how about directly optimizing the evaluation metric for retrieval? So common measures are recalled top K results, precision at top K, and mean average precision. The main problem here is that they're not differentiable. And so common practice to use them in training is to have a differentiable surrogate that can be used in an end-to-end way. So this has been the case for average precision with a few approaches in the literature. And the following, I will present our own recent work on optimizing recall and top K results. So now simply go through how recall at K is computed, similarity of the query with its database image is computed, then all the database images are ranked according to the similarity, and then recall at K is simply the number of positives that are in the top in the K top ranked positions over the number of all positives in the database. Let's now see this from a slightly different perspective. Okay, what we need is to compute the position of each database image in the sorted list. So let's, for instance, focus on the third image in this example. So its similarity to the query is compared with all other similarities of all other database images. And if this difference is smaller than 0, then that means that another image is ranked before this one. And we need to count all these cases. So this is done by feeding this difference to a step function. And then we get the output of the step function. We sum the values. Simply +1, it is the position of this image in the ranked list. So now that the ranking of each image is obtained, now what we need to see is how many of these images are ranked within the top K. And as before, we subtract this, the position of each image from the value of K, feed it to a step function, sum the outputs, and then one can directly obtain recall at K. Now, why is this different view of estimating recall useful? Well, mainly because we can approximate. We can instead approximate this function by using a sigmoid, and therefore we end up with a surrogate that can be used during training in end-to-end manner. Now, recall depends on the whole database, and using a large database in the training is challenging because of the constraints that training with mini batches has. So to handle this, we follow the approach of Revaud et al. So what's happening there is that first a forward pass is performed to obtain all embeddings, while intermediate tensors are discarded from the memory. Then the loss is computed, and so are the gradients with respect to the embeddings. Finally, each of the embeddings is recomputed. There is a second forward pass. Okay, that's the extra cost here. But this time we are allowed to perform backpropagation of the gradients. So, and this, despite the double cost of the forward pass, this allows us to train with several thousands of large resolution images inside the single batch. And as far as I know, online implementation of this approach does not exist, but it will be released with our code. Okay, now here comes the point that I'm about to talk about how to obtain training data in the form of matching and non-matching pairs to train with the earlier mentioned pairwise losses. So first source of supervision are the GPS coordinates, the GPS labels in this case. So we can easily find non-matching pairs because images are far enough according to GPS coordinates. Now for the matching pairs, it is a bit trickier. And this is because we know the locations. So we know that images are nearby, but the camera orientation is unknown, and nearby images might still be depicting something different. So to resolve that, Arangelovic et al. Pick the nearby image that has the closest descriptor according to the network in the current training epoch. So this indeed resolves the ambiguity and picks true positives, but in most cases they are not challenging enough for the network to improve. Another rich source of training data that comes for free is structured from motion with classical approaches. So 3D models of popular landmarks and buildings are created without any supervision, given a large crowdsourced dataset. The full geometry of the scene in this case is known, and we can use it to sample positives that are known to depict the same objects, the same view of the landmark. And let's see this in more detail. So we have an anchor image from one 3D model, and all images from other 3D models can be considered as non-matching. So picking the one with the most similar CNN descriptor, global descriptor, is the hardest negative. So in the case we need more negatives, picking the k hardest ones is often redundant. And we simply fix that by picking the single closest descriptor per 3D model, and then obtain a more diverse set of negatives. And actually, hard negatives are quite common in the literature for many different tasks, but hard positives are not. And this is because of the large intra-class variability. Once more, SFM allows us to work on that, and given an anchor image from a 3D model, other images of the same 3D model are candidate positives, but not also the same object. So if we resolve this ambiguity by choosing the image with the closest descriptor, as we did before, we pick a true positive, but not a very challenging one. So now if we choose based on the high number of inliers, then this is a more challenging example, since the global descriptor is not necessarily already close enough, but still it will be pushed closer during the training. And to increase the hardness, we randomly pick a positive out of a set of positives that have more than a fixed number of threshold of inliers. Now let's see how the hardness of these training examples affect the training. So we start with MAC descriptors from a network that is pre-trained on ImageNet, and then train with contrastive loss and obtain significant improvements. While if we use the diverse set of negatives, we get an extra boost, and a larger one if we use the hard positives from SFM, and making them more challenging gives the final boost. So actually having an automated way to obtain clean and challenging pair labels seems to be important. And the same holds in the work of Gordo et al., where they're fine-tuning the RMAC global descriptor. They start from labels at landmark level, but these include multiple viewpoints, indoor and outdoor views, and so on. So there they're using bug of words and special verification to clean the dataset and find the ones that depict the same view. So what is interesting to see in their experiments is that classification loss is consistently worse than the pairwise loss. And moreover, cleaning is not required with classification loss because it can deal with a large intra-class variability. So another approach that tries to handle location recognition as classification is Planet by Google. The Earth is partitioned into about 26,000 cells, and the training is performed with cross-entropy loss. So the impressive achievement in that case is that they managed to obtain a model for Earth scale predictions that is super compact. But the question is it better than instance search? So the answer is given by a CVPR 17 paper, where they evaluate Planet and more models at different scales. So the scales are street level or city level, which are close to the scope of this tutorial, of this part of the tutorial. And then they have also coarse scales such as region, country, and continent. So the model that is trained with classification loss is the best at coarse level, but very bad at fine level. Apparently, it can capture common characteristics of big regions, but does not memorize every single instance. Now, if the internal global descriptors from this model are used as descriptors for instance search, then the recognition improves a lot at the case of fine level. Now its image is memorized through the process of indexing. And well, as a drawback, this approach, of course, requires more memory. Then what they tried in this work is to improve the classification model by further fine-tuning with a pairwise loss, with a metric layer loss, but got no improvements. And it seems that the large intra-class variance is once more a problem. So trying to solve this with positives by the trick of picking the closest descriptor did not result in challenging enough pairs. And at the end, what they tried is our earlier model that is trained on SFM, and these descriptors were used for instance search, providing the best results at fine level. So of course, this comes at the cost of extra memory, but it seems that instance search is the thing to do for accurate location recognition in this setup. And another benefit of instance search is that if at some later stage there are new database items that are available, one can integrate them and index them, and without the need to perform any further training. So I think that's the moment where I will speed up a bit. Okay, so here I wanted to summarize some observation from some of participation of our team in a Google Landmark Recognition Challenge, where we got the best of each world, global descriptors, and dealt with SNK back then. So I will skip most of my results, mainly to say here that recognition is performed with a Kenyan classifier by simply exploiting the top-ranked images. And combine the similarity scores of the two approaches actually gives a significant boost. So the intuition here is that each of the approaches acts on a different part of the precision recall curve. You have special verification with local descriptors that improves precision by strong verification, while GEM improves recall for cases that point correspondences do not work. And then once more, kind of speeding up and going more briefly. When I upload my slides, I will include some more examples. Now, briefly some time to talk about the final step, which appears to be crucial in instance search with global descriptors. And that's the part of whitening. So we obtain a global descriptor. So this is now fixed. We have a network that where we finish the training, or it was already pre-trained, and now we process it with PCA whitening. So what is common is to do first PCA on our descriptors. We center and rotate, and even though reduction is possible, let's assume that we're keeping all dimensions. So PCA just by itself is not that useful. So what was happening with classical approaches, a common normalization is parallel normalization, where in a component-wise manner, we apply a power and preserve the sign. So now with PCA, co-occurring features are mapped to the same component of the final vector. And what does parallel do is co-occurring features will be jointly downweighted. And in this way, any undesirable overcounting of co-occurrences is somehow handled. And this is what happens in an improved way with PCA whitening, that now we're downweighting each component, not with just a fixed power, but according to the corresponding eigenvalue. I'm going a bit fast here. And then this generalized approach where we have hyperparameter t. For t equals 0, we have it's simply equal to PCA, and for t equals 1, it is equivalent to the full whitening, while for intermediate cases, we do not end up with a unit covariance matrix. So still in all these cases, there is no supervision involved. We have a set of descriptors which we use to learn the PCA. Now, if supervision is there, we can do better. Actually, we separately create the positive covariance from matching pairs and negative one from non-matching pairs. Then we estimate the whitening on the positive covariance. And this is as if we would be learning Mahalanobis distance based on the positives. And then in this whitened space, then we can still learn rotation by PCA and reduce the dimensionality if needed. So just a quick look at quantitative results when we do that. So we're using a MAC descriptor with a pre-trained network. PCA with parallel already gives a significant boost. PCA whitening seems to be better. If we use the shrinkage with the tuning of the hyperparameter t, it's even better, while at the end, the variant with supervision is the top performing case. And compared to the initial score, there is a big boost in performance that happened without any change in the network parameters, just by this last post-processing block. And the same holds for other descriptors, like with some pooling or gem descriptors, and also the same holds even if we're using fine-tuned representation. So what we see here is that actually the benefit is different among different pooling operations, which is not so easy to interpret. We have some better interpretation in a different context from our earlier work, but I wasn't planning anyways to go into details about that. So now just concluding and trying to maybe list the main lessons to keep from this presentation is that handling place recognition as instance search is better than handling it as a classification task. So while classification losses can better handle the large intra-class variability, while pairwise losses will do good, but they need selection of clean and challenging enough pairs. And global descriptors and voting approaches with local descriptors stand on different parts of the trade-off between speed and performance or memory and performance. And we should probably not ignore how important this trade-off is and focus on more aspects than the performance itself. So thank you for your attention. This slide just includes some link to open source code for some of the methods that I described. And since I'm a bit over time than what was planned, I can go in the chat right after and answer any questions.
Yorgo, thank you very much. There are a couple of questions that I could tell you if you could answer on the spot. One is, how do the classical descriptors such as shift-safe compare with modern deep learning-based descriptors? And the other one is it possible to use similar approaches for visual indoor localization? If you want to say something.
Okay, I will go very briefly just for the first one. So for instance, we had some comparisons in our CVPR 18 paper, where we revisited Oxford and Paris benchmarks. And it was clear there that, for instance, back then it was the DELF approach that was performing significantly better than the classical ones. Now, this is when we're talking about the input local descriptor set, while when we also talk about classical, I also included actually the matching process that was borrowed back from this classical period and this classical approach. So now about the second, I would say the second question, definitely yes. Maybe more is about to follow in the other parts of the tutorial. So if you're interested about coarse localization, definitely yes. But now the other part will cover this if doing it in the retrieval way is precise enough and in what cases it is accurate enough. So Yanni, maybe you can start sharing your screen and we can continue with your part.
Can you see it?
Yeah, seems good.
Okay. I will talk about some special topics on metric learning, including knowledge transfer, data augmentation, and attention. So the overall context is that, as we have seen, representation learning for instance level tasks like visual localization often reduces to metric learning. There are many ideas that are addressed most commonly in classification and less so in metric learning. Those include knowledge transfer, for example, from teacher to student models, data augmentation, and one powerful recent way is mix-up that we're going to see. And finally, attention in the form of spatial or channel attention or global or local attention that we will see in the last part. So all three parts are three works of my team and collaborators, but through them, we will be able to see many interesting ideas. So we begin with knowledge transfer. And this work is called Asymmetric Metric Learning for Knowledge Transfer, co-authored by Mateusz Budnik and myself. This work has been presented in CVPR 2021, and code is available. So we are focusing on instance level image retrieval, and we introduce a new asymmetric testing task. An image database is represented by a large network, while queries by a lightweight network. Rather than reindexing the whole database, it might be preferable to adapt different smaller models to different end user devices. So inspired by this task, we introduce asymmetric metric learning, where we use asymmetric representations training in a teacher-student setup. This applies to both symmetric and asymmetric testing and combines knowledge transfer with supervised metric learning. So in the following diagrams, we denote the student by F theta, where theta is the learnable parameters, and by G, the teacher. In black is an anchor, and in green is positive examples. In red is negative examples for this anchor. So in the standard symmetric form of supervised metric learning, labels are used, but not the teacher. Positive pairs of examples are mutually attracted, and negative pairs are repulsed in the student space. In contrastive loss, for example, independently, positive examples close to the anchor are pushed closer to the anchor, and negative examples are pushed further from the anchor by some margin in the student space. In the triplet loss, positive examples are pushed closer to the anchor than the negative by some margin in the student space. In the multisimilarity loss, positives farthest from the anchor and negatives closest to the anchor receive the greatest relative weight. Conversely, one may use the teacher, but not the label. Examples in the student space are attracted to corresponding examples in the teacher space. By regression, for instance, representations of the same example by two different models should be close to each other, where the teacher is fixed. More generally, one may use pairwise or groupwise relations like distances, angles, or ranks, encouraged to be compatible in both spaces. In relation knowledge distillation, there are measurements of the same examples by two different models that should be close to each other. Those measurements includes, for instance, distance or angle, and regression is a special case where the measurement is actually the embedding of the anchor itself. In dark rank, examples that are mapped farther from the anchor than a given example X in the teacher space should do the same in the student space. So basically, this encourages different kind of ranking. This encourages the same ranking in the teacher and the student space. Ideally, we would like to use both the labels and the teacher. For example, anchors in the student space should be attracted to positives and repulsed from negatives in the teacher space. In asymmetric metric learning, we simply use the asymmetric similarity of two examples by the two different models with any supervised metric learning loss. It turns out that regression and asymmetric contrastive are the best choices. We combine them into what we call contrastive plus. This means that the anchor itself is treated as a positive, which would make no sense in standard supervised metric learning, but now it makes sense because the similarity is asymmetric between two different models. We use revisited Oxford and Paris as a test set for image retrieval. As a training set, we use structure from Ocean 120K, where positives are determined by camera position and number of inliers according to shift descriptors, whereas negatives are mined as k nearest neighbor from non-matching clusters according to the learn descriptors. We use ResNet 101 as a teacher and EfficientNet B3 as a student. After adapting the dimensions of the student to the teacher, the student still has 7 times less flops and 3 times less parameters than the teacher. In symmetric testing, when the student is trained alone, it performs below the teacher by a large margin. By adapting the dimensions, the margin is reduced. Contrastive and contrastive plus perform best among supervised loss function, while regression performs best among unsupervised. We use hard negative mining with supervised losses, while asymmetric indicates the new solutions. Importantly, by contrastive and contrastive plus, the student beats the teacher. Regression is second best, where the student is only slightly below the teacher. Interestingly, everything else fails in the sense that knowledge transfer is worse than training the student alone. In asymmetric testing, regression is the best, but it's significantly lower than the student alone. Contrastive and contrastive plus are second and third best, but significantly lower than regression. So this is a much more challenging problem. Relational knowledge distillation and dark rank fail completely, which is expected because we really need absolute coordinates for asymmetric testing. We need the teacher and the student descriptors to match in the same space. Triplet and multisimilarity also fail completely, and this is more unexpected. We can use this visualization to see why certain methods fail. So here we have 5 classes from the Oxford dataset and 20 easy examples per class. We visualize them with TSNE embeddings from the student network. So here we see on the right that triplet multisimilarity, relational knowledge distillation, and dark rank fail completely because the teacher and the student embeddings are far apart, whereas contrastive plus, and regression on the left, we see that teacher and student embeddings are in good correspondence. So we can use the features of one network to search into a database indexed by another. So we go to the second topic, that is data augmentation. And here we will study mix-up for deep metric learning. The paper is on arXiv and the code will be published upon publication. So in general, data augmentation increases the amount and diversity of data, improving the generalization performance at almost no cost because we perform different data augmentation in every epoch. However, it operates on one image at a time, and it is limited to label preserving transformations, which means that it's hard to explore beyond the image manifold. Mix-up is a recent method that operates on 2 or more examples at a time, interpolating examples and labels. So this is much more powerful in order to explore beyond the image manifold. In classification, it smooths decision boundaries far away from the training data, and it reduces overly confident predictions. But how about metric learning? It has not been explored much. So the standard mix-up operation is a linear interpolation. We are given two inputs, x and x prime, that can be anything like examples, embeddings, or the labels. And we are mixing them with some interpolation factor lambda, which is drawn from a beta distribution. And it's a linear interpolation. From x and x prime, we obtain lambda x times 1 minus lambda x prime. To interpolate examples, one may decompose a model F as FM composition GM. So GM maps from the input space to some intermediate feature space, and FM then maps to the final embedding. By using this decomposition, we can mix the input images, for example, x and x prime, before mapping through F, and this is input mix-up. Or we could map to the intermediate feature space, mix, and then finally map to the final embedding. And finally, we can map the inputs directly to the final embedding and then do the mixing. This is the embedding mix-up. Labels are typically mixed by the standard mix-up operation, which is linear interpolation. In classification, labels are represented by one-hot encoded vectors. And it is those vectors that are linearly interpolated, and there is one such vector per example. In metric learning, labels refer to pairs of examples, so it is less straightforward how to properly perform mix-up in metric learning. Existing approaches have been applied to deep metric learning, and separately also to self-supervised contrastive learning. Our approach refers to deep metric learning. It is important to respect certain properties. First, that there is a stochastic sampling of the new mixed examples to be generated. Second, we should be able to work both with pairwise losses and proxy-based losses that are very common in metric learning. More importantly, we should be able to sample from different classes so that we have more than one labels for the mixed examples. And even more importantly, we should be able to mix the labels themselves, because there are several approaches that mix examples or features, but not the labels. And finally, it is important to be able to mix anchors with negatives, because we have seen that this improves performance. So our approach has all these properties. We compare to a number of existing approaches, but here we don't focus on this comparison. We focus more on the ablation, on how mix-up improves different state-of-the-art losses. So our approach is called metrics for metrics mix. And it allows an anchor to interact with positive examples in the same class, negative examples in different classes, and also interpolated examples. So here we are interpolating between two negative examples, and this means that the interpolated example is also negative. But importantly, we also interpolate the labels. So now we can interpolate between positive and negative examples, and we have interpolation of the label too. So it is not, the new example is not just positive or negative, but can be anything in between. How to do that? Well, we begin with two examples of contrastive loss and multisimilarity loss. And we form a generic loss because we want to apply mix-up to in a way that is generalizable across many different losses. So we introduce this generic loss where we can see that the similarity between the anchor and positives and negatives is going through some nonlinear function first, which we denote as rho plus or rho minus for the positive and negative respectively. And then we have a summation over all positives or negatives, followed by another nonlinear function that we denote as sigma plus or sigma minus. There is no such function for contrastive loss. It is linear in this sense. Now, with this generic model, different loss functions can fit into this formulation, including contrastive, multisimilarity, proxy anchor, proxy NCA, or proxy NCA++, which are recent methods. Now, in order to be able to mix the labels, there are two more steps to go. One is that we need to combine positives and negatives in one set. We do this by attaching labels to them. So for every positive, we attach a label of 1. And for every negative, we attach a label of 0. Now the summation runs across one set, the same set U of A, that is all positives and negatives of a given anchor. And for each example, we multiply by y if it is a positive and by 1 minus y if it is a negative. In this form, the second step is to introduce mixed examples. So we perform mixing in either the input or the feature or the embedding space. And we also mix the labels. Now the labels are scalars, and we allow them to be anywhere between 0 and 1 by just linear interpolation of the original labels. And so the form of the loss function remains exactly the same, only we have a new set of inputs and labels, and we use the embeddings V instead of the inputs X directly. So this is all the idea. And this we try on a number of datasets for deep metric learning, which include fine-grained classes, for instance, of bird species, car models, different online products, and also fashion, including many different classes and attributes. So we observe that overall, we get small consistent improvements over all loss functions that we have worked with. But more importantly, we get a much larger improvement, up to 3 or 4%, with contrastive and multisimilarity loss. It turns out that multisimilarity, when we add mix-up, improves and it becomes better than state of the art. It's better than proxy anchor and better than proxy NCA++, which were previously outperforming multisimilarity. So it is important that mix-up actually changes the relation between state-of-the-art methods, state-of-the-art losses. One interesting aspect is positivity. So we define a mixed embedding as positive for a given anchor if minimizing the loss contributes to decreasing the similarity between the two. So this means that the partial derivative of the loss with respect to the similarity is non-positive. Under certain assumptions, we estimate the probability of positivity for a single mixed embedding as a function of the interpolation factor lambda. And then we measure empirically the positivity as a function of lambda. And we have this nice sigmoidal form of positivity going from 0 to 1 as lambda goes from 0 to 1. This is a very nice interpretation of how some mixed examples behave not as positive or negatives, but as something in between. And this brings us to attention, the final part, where I will be really brief. If you could let me know how much time there is, because I didn't keep track.
Yanni, maybe a couple of minutes would be okay.
Okay. So this is a global local spatial channel attention for image retrieval. This work will appear on WCV 2022. So we start from any input feature tensor from a backbone, and we consider two different kinds of attention. One we call local or first order, where elements of the feature tensor, channels or locations, are weighted independently by some form of pooling. And the other is global or second order attention, which involves pairwise interaction between elements. It's the common form of attention that is used in transformers. And we also consider both channels and spatial locations in the attention. So this gives rise to four different forms of attention. One is local channel, where pooling over locations yields weights on channels. Then there is local spatial, where pooling over channels yields a spatial attention map. There is global channel, which allows pairwise interaction of channels. And finally, global spatial, which allows pairwise interaction of locations. So we combine all four forms of attention on a given feature map, and then we fuse the two different streams together with the original feature tensor. We apply this to image retrieval. We have a ResNet 101 backbone, and we use global descriptors only. I won't go through the settings of the experiment, but we train on the large Google Landmarks V2 clean dataset, which gives very good performance. And we perform an ablation of all different combinations of attention. It turns out that channel and spatial attention might be harmful if when used alone, but they are complementary and surprisingly beneficial when used together. And also local and global attention are clearly complementary, and the gain is nearly additive. So we get overall somewhere between 4 and 10% improvement by just using this extra module on top of the network. So this completes my talk, and thank you very much.
Hi, Yanni. So thank you for the talk. Maybe, okay, I don't see a question at the moment. So maybe one from me. So about the last part of attention, would you say, okay, in the methods that I was presenting earlier, for some of them, there is some interpretation about how are you actually matching the separate activations in the feature map, right? Different positions. So is there something that one can tell when you include an attention in the way you do?
Are you referring to the fusion in the end?
I'm referring to the overall architecture, you know, starting that you have an input feature map F there.
Mm-hmm.
So for instance, at the end of the day, when you have two global descriptors, dot product between them, if there is any interpretation about how does the attention
I see what you mean.
affect the final similarity.
Well, yes, I see. We haven't worked on this, but I'm pretty sure that by following in the backward path, there must be some interpretation to be studied. So it would go first to the spatial attention, which is maybe the most interesting, and then backward to the channel attention. So I'm pretty sure that those spatial attention mechanisms have been studied independently. This is the combination that we study here. So any interpretation that would apply to local spatial or global spatial would apply also here.
Okay, thank you.
Thank you very much.
So, okay, maybe we're ready to move to the second part of the tutorial, switching gears, talking about precise localization, starting with Susanna's talk. Okay, Susanna, you're sharing your screen. Everything seems good. Okay. You're muted. Okay. You're muted.
Okay, so now it should be okay. Hi. Okay, so welcome to the second part of the tutorial. So in this part, we are going to look at feature-based visual localization techniques. These algorithms usually establish 2D to 3D matches between features in a query image and 3D points in the scene. And these matches are then used to estimate the camera pose. And this is usually done by applying some absolute camera pose solvers inside the ransack loop. So in the following, I will just give you an introduction to camera pose solvers, especially these absolute camera pose solvers. Camera geometry problems like relative and absolute pose estimation are core problems in computer vision with many applications. For example, the mentioned visual localization, 3D reconstruction, SLAM systems, augmented and virtual reality, and autonomous driving. In all these applications, we need to calibrate our cameras, we need to estimate their positions. Camera geometry solvers are usually used inside ransack-style hypothesis and test frameworks. Here, the number of samples that needs to be tested exponentially grows with the number of points or lines used for the estimation. For efficiency, it is therefore important to employ minimal solvers that generate a solution from a minimal number of point or line correspondences and using all available constraints. Moreover, such minimal solvers return correct geometry, for example, correct rotation matrices, since they are using all available constraints. These solvers are used inside ransack to obtain initial estimates of the geometry and the inlier set. On the other hand, non-minimal solvers are usually used for refining pose estimates and inlier set in local optimization, for example, in LO ransack. As I have already mentioned, camera geometry solvers are core components of localization as well as 3D reconstruction structure for motion pipelines. In this tutorial, you will see a lot of nice examples and videos from localization applications. So here I will show you one video from closely related applications, 3D reconstruction from images. 3D models like the one that you can see in this video are important parts of the feature-based localization pipelines that will be discussed later. Here you can see an example of a large-scale 3D reconstruction. This reconstruction was created using Reality Capture, a 3D reconstruction software from Capturing Reality, a startup company founded by my former colleagues from CTU in Prague. In this case, this 3D model, so this 3D point cloud was created from almost 30,000 images, and the final 3D model contains more than 100 million triangles. And this software uses different camera geometry solvers for calibrated as well as uncalibrated or partially calibrated cameras, including solvers that I will briefly present in this talk. In this talk, I will focus on absolute pose solvers, since these solvers are more frequently used in localization pipelines. However, I will briefly review relative pose solvers, because also these solvers are important. For example, we are using them when we are creating 3D models like the one that you have seen in the previous video. In relative pose solvers, we want to estimate the unknown relative rotation and translation between two cameras or a motion of a camera. This problem is also known as the problem of estimating epipolar geometry. Relative translation can be estimated only up to scale. Therefore, for calibrated cameras, we have 5 degrees of freedom, 3 for the unknown rotation and 2 for the unknown translation. The first solution for calibrated perspective cameras that uses the minimum number of 5-point correspondences was proposed by Krupa already in 1913. And this method returns up to 11 solutions to the problem. In 1981, Long and Higgins introduced the notion of the essential matrix, and together with a non-minimal method for its estimation from 8-point correspondences. In 1988, it was shown by Demazur that this relative pose problem for calibrated perspective cameras has actually at most 10 distinct solutions. Later in 2004, Nister developed the first algorithm that guarantees to indeed provide at most 10 solutions. And this algorithm is extremely efficient. It solves only one polynomial of degree 10, and it runs approximately 5 microseconds. This algorithm from 2004 is the state-of-the-art solution to calibrate the relative pose problem. Nister's 5-point solver requires that the two cameras are calibrated. After the introduction of Gremner bases to the computer vision community and efficient algebraic solvers, it was around 2005, there has been quite some work on relative pose estimation for partially calibrated cameras, for example, cameras with unknown focal and unknown radial distortion. Moreover, new solvers are still appearing. For example, recently, Magnus Oscarsson, in his OmniCV 2021 paper, revised different relative pose solvers for cameras with unknown radial distortions, and he proposed some new solutions that are more efficient than the existing solutions. Sometimes, especially for more complex geometries, minimal problems can result in quite complex systems of polynomial equations. For some problems, for example, the problem of estimating the relative pose between two cameras with different radial distortion parameters, non-minimal solutions, especially minimal +1 solvers, can be orders of magnitude faster than minimal solvers. Therefore, for a wide range of outlier ratios, such non-minimal solvers can result in faster ransack times, as their higher efficiency more than compensates for the large number of iterations that we need to do in ransack. So sometimes it's better to use minimal +1 solvers than minimal solvers. Despite recent progress in creating efficient polynomial solvers, for some relative pose problems, for example, the relative pose problem for rolling shutter cameras, efficient solutions are not known. The main reason is that these problems result in very complex systems of polynomial equations that are not efficiently solvable using existing methods, even after using, for example, minimal +1 points. Okay, so now let's move to absolute pose solvers. Absolute pose estimation is the problem of determining the position and orientation of the camera from an image of a known object or scene. This problem actually predates modern cameras. For example, already in 15th century, Leonardo da Vinci wondered how to determine a painter's eye viewpoint from a perspective painting. And later in 1715, Taylor, also known for the concept of Taylor expansion, developed an algorithm for estimating both the focal length and principal point of an imaginary camera or an observer from an image of a cuboid, together with the side lengths of this cuboid. So in some sense, this is a very early prototype of modern solvers that jointly estimate the camera intrinsics and also extrinsics. So let's first look at the case where the intrinsic calibration of the camera is known, so absolute pose solvers for calibrated perspective cameras. In this case, we want to compute the unknown rotation and translation that transform points in the world coordinate system into the local coordinate system of the camera. We do have 6 degrees of freedom, 3 for the unknown rotation and 3 for the unknown translation. Each 2D to 3D point correspondence gives us 2 constraints in the form of the projection of the 3D point into the image. The constraints have the form shown here on the left. So this is the well-known projection equation with unknown rotation and translation metric vector, and alpha I are the depths of unknown depths of points 3D points xi. Since we have 6 degrees of freedom, the minimum number of 2D to 3D point matches necessary to solve this absolute pose problem for a calibrated camera is 3. And the resulting solvers are known as P3P solvers, so well-known P3P solvers. P3P solvers have a long history. Already in 1615, Snellis provided a solution for the case where the 3D points and the camera lie in a plane. Lagrange in 1773 was the first to sketch a general P3P solver, a solution to the general 3-point pose problem. Another well-known solution is the solution from Grunert from 1841. And in computer vision community, one of the best-known solutions is the one by Fischler and Bols introduced in the ransack paper. Despite this history, P3P solvers are an active field of research with the current state-of-the-art method proposed only recently, 2018, by Persson and Nordberg. P3P solvers for calibrated cameras are extremely efficient. For example, the solver by Persson and Nordberg only requires approximately 250 nanoseconds. Therefore, P3P solvers are used in many applications, so they are really widely used. However, in many situations, the internal camera calibration is unavailable or only approximately known. Examples are, for example, 3D reconstructions from photo community collections, which often do not provide camera intrinsics, localizing images downloaded from internet, historic photos or paintings, or handling zooming cameras with variable focal length. This creates the need for jointly estimating the camera pose and the camera intrinsics. So let's start with a case where only the focal length of the camera is unknown. This is a reasonable assumption, since principal point and skew can usually be considered as known or approximately known. The projection equation for an uncalibrated camera with unknown focal length has the following form, as you can see here. Here R and T are the unknown rotation and translation, F is the unknown focal length, and alpha I is the unknown depth of the point xi. So in this case, we have 7 degrees of freedom, and each point correspondence gives us 2 constraints. Therefore, we need 3.5 point correspondences to solve this problem. Compared to the P3P problem, the resulting system of equations is more complex because we are multiplying with our rotation metrics with unknown focal length. For planar scenes, this problem was solved by Abidi and Chandra already in 1995, and in 1999, Trix proposed the first solution for non-planar scenes. Compared to these earlier solutions, Bunyak et al. Introduced the first robust and efficient general solution, and this solver uses efficient Grubner basis to solve the system of nonlinear polynomial equations that we have in this problem. These solvers are non-minimal in the sense that they use constraints from 4-point correspondences. And there are 2 truly minimal solvers that only use 3.5 point correspondences, one by Wu and one published recently by Larson. The currently most efficient solution to this problem of estimating absolute pose of a camera with unknown focal length is based on an efficient way to compute the solutions to a system of 3 quadratic equations with 3 unknowns. Such solver is known also as 3Q3 solver. The resulting solver needs only approximately 2.3 microseconds, and it returns up to 8 solutions, but is restricted to non-planar scenes. However, since this solver works really well for close to planar scenes, this is usually not an issue in real applications, and such solver is really useful for such real applications. A good implementation of this solver is available in Victor Larsson's POSLib library. In many situations, using wide field of view cameras offers advantages. For example, more stable pose estimates, the ability to observe a larger region of space, and therefore high robustness to occlusions and illumination changes. In order to cover a wider field of view, these cameras usually exhibit large lens distortion dominated by radial lens distortion. Since we might not be able to calibrate our cameras in advance, this creates the need for absolute pose solvers that can handle unknown radial distortion. The projection equation for an uncalibrated camera with unknown radial distortion and unknown focal length using so-called 1-parameter division radial undistortion model has the following form here. Here lambda is the unknown undistortion parameter of this division model. This 1-parameter division model is very popular, and it's used in almost all minimal solvers since it provides a good trade-off between model accuracy and model simplicity. And since it can, with 1 parameter, handle even large radial distortions, for example, a distortion that appears in GoPro cameras. So in this case, we have 8 degrees of freedom, and since each correspondence gives us 2 constraints, we need 4-point correspondences to solve this problem. This problem was first solved in 2009 using the Grubner basis method, and the final solver was really huge. It was performing Gauss-Jordan elimination of a matrix with more than 1,000 rows. Since then, the problem was revisited several times, and in 2017, we proposed a solution based on the elimination ideal method that performed Gauss-Jordan elimination of a quite small matrix of size 40 × 50. So we managed to really simplify the solver. Still, this solution may not be the best for real-time applications. However, in 2013, we proposed a solution that uses 5 instead of 4-point correspondences, so not a minimal number of point correspondences, but minimal +1. And this solution uses a 2-step approach based on so-called Y&V radial cameras, where we first estimate the pose up to an unknown translation along the principal axis. You can see illustrated in this picture on the left. And then we jointly solve for the translational degree of freedom, focal length, and up to 3 distortion parameters by solving a simple linear system. So the final solver is very efficient, and it runs in less than 2 microseconds. And therefore, inside runtime, it is more efficient than the 4-point minimal solver for a large range of outlier ratios. Recently, we extended this 2-step approach to rational radial distortion models of arbitrary degree for both distortion and undistortion. Distortion models allow for easier computation of reprojection errors in image space than the undistortion models that are used in most minimal solvers. Therefore, such distortion models are useful, for example, for structure for motion or augmented reality. In 2017, we used the same two-step approach based on these 1D radial cameras to solve the absolute pose problem for a camera with unknown focal length, radial distortion, and unknown principal point. This solver uses 7-point correspondences, and with this solver, we can register even cropped images downloaded from internet, like the images shown on this slide. And my favorite here is the image of the back with an image of Notre Dame Cathedral printed on it. So we were able to register even such artificial picture or cropped picture. Okay, so let's move to rolling shutter cameras. Nowadays, almost all cameras are equipped with rolling shutter since they are cheaper and easier to manufacture. Rolling shutter sensors capture images line by line, leading to distortions when camera or scene moves during the image capture. In this case, each line is potentially captured from a different pose. Therefore, the final projection is not a perspective one, and it has to be modeled using a more complex geometry. Since rolling shutter cameras capture each row at a different time and potentially from a different pose, camera rotation and translation are therefore functions of the image row. So our projection equation looks like this, where our rotation and translation are functions of the image row Ri. Camera rotation and translation can be decomposed into the initial camera pose R0 and C0 and the motion during the image capture. In real applications, the translation can be approximated by a constant velocity model, and for realistic motions, it is usually sufficient to linearize the camera rotation around the initial rotation R0 using the first-order Taylor expansion. And with these approximations, the rolling shutter projection equations has the following form, as you can see here. And such a model has 12 degrees of freedom because we have 2 rotational matrices and 2 translational vectors. And even for fully calibrated rolling shutter cameras, it results in a quite complex system of polynomial equations, highly nonlinear equations. So this model was unsolved, and we solved it only recently in 2020. And the solver that we proposed in this PAMI paper uses different tricks to simplify the input equations, and it runs approximately 1.4 milliseconds. 1.4 milliseconds is still quite slow for being applied inside RANSAC. Therefore, an additional approximation was proposed in calibrated rolling shutter absolute pose solvers. This double linearized model uses a linear approximation to the initial camera orientation R0. While camera motion during the image capture is usually small and can be linearized, the initial camera orientation can be of arbitrary magnitude, and therefore it can be far from the linear approximation. A practical solution for calibrated cameras is to first compute a rough approximate pose with a fast standard global shutter P3 solver, and then the object coordinate system is aligned to it, so that the remaining rotation is close enough to identity, so we can use this linearization. The solver to this model, double linearized model, is of course simpler than the single linearized solver, but still not useful for real-time applications as it runs approximately 0.3 milliseconds. Therefore, in 2018, we proposed a solution where we combine an iterative scheme with fast solver to a simple system of linear equations. So in this case, to simplify our equations that look like this solver does the following. So in each iteration, we fix the camera orientation unknowns V, these blue unknowns, in the nonlinear monomials. These are our nonlinear monomials that appear in our equations, W times V, skew-symmetric matrix W times skew-symmetric matrix V. And we fix these camera orientation unknowns to the estimates from the previous iteration. And therefore, in each iteration, we solve a simple linear system. So we linearize our equations in this way. And this solver usually converges in a few iterations, something like 3-4 iterations, to the solution of the original system. And its total running time is something like 10 microseconds. So it's much, much faster than the original solver. And therefore, it can be used in real-time applications. And now let's look at the most complex case, so where both the focal length and the radial distortion parameters of a rolling shutter camera are unknown. So in this case, we have completely uncalibrated camera, rolling shutter camera in some sense. In this case, rolling shutter projection, even after linear approximation of the camera rotation, the motion during the image capture, and the initial camera orientation, so using this double linearized model, results in a complex system of polynomial equations that is not solvable using algebraic methods. So the solvers are extremely slow and unstable. However, in 2020, we proposed a solution that was based on a similar idea as the iterative linear solver for calibrated rolling shutter camera. Here in each iteration, we again fix some unknowns in nonlinear monomials to the estimates from the previous iteration. By fixing them, we don't have linear system. We have still nonlinear system of polynomial equations, but much simpler system. And in this way, we combine this iterative scheme with fast algebraic solvers for this simplified and tractable system of polynomial equations. The final solver is simple, fast, and it usually converges in less than 10 iterations. And in each iteration, it solves a simple system of nonlinear polynomial equations using the Grobner-Basis method, and one iteration runs approximately 40 microseconds. This solver outperforms the only competitive solution, which first calibrates the camera using a global shutter solver, and then uses a calibrated rolling shutter solver and local optimization to find the final solution. As you can see here, in these tables, our solver returns more inliers and smaller focal length errors than the baseline. So our solvers are these last two columns, and the baseline is first two columns. Here is also one example of an input image on the left, and the undistorted image is generated by our method on the right, and this baseline in the middle. And as you can see, this baseline is not able to properly undistort the input image. Finally, I will briefly present semi-generalized pose solvers that can be an interesting alternative to absolute pose solvers in visual localization pipelines. The semi-generalized relative pose problem is the problem of estimating the pose of a pinhole camera, so this red camera here on the right, with respect to a generalized camera consisting of multiple pinhole cameras with known relative poses, so these blue cameras here. Therefore, in contrast to standard relative pose problems, in this case, the scale of the translation can be recovered. And compared to absolute pose solvers, the semi-generalized solvers use only 2D to 2D point matches, and therefore we do not need to store a 3D model of our scene, which may be useful in some applications. A disadvantage is that these problems result in more complex systems of polynomial equations than standard relative or absolute pose problems. So our equations in this case look like this. In this case, we need 6 2D point correspondences to solve this problem for a calibrated camera, and 7 point correspondences for a camera with unknown focal length. This problem was solved in 2015 by Zheng and Wu. However, due to a complex system of polynomial equations, they only propose solutions to several specific configurations of points in the generalized camera. For example, this solver requires 4 or more points coming from the same camera of a generalized camera, and moreover, solvers that can handle 3 cameras, like this E4+2 and E5+2 solvers, are too slow for real world applications, with running times more than 1 and 13 milliseconds. This is maybe the reason why these solvers are not used in practice in visual localization pipelines. In ICCV this year, we propose solution to this problem for planar scenes, and in this case, we need 5 2D to 2D point correspondences to solve this problem for calibrated as well as a camera with unknown focal length. Also, for this semi-generalized homography, the original equations are quite complex. So in this case, we have equations of this form that you can see here, with unknown rotation, unknown translation, unknown focal length, this calibration matrix K, and also unknown normal of the plane. So we have significantly more complex equations in 9 unknowns, or actually 10 unknowns for partially calibrated cameras that are not really solvable, efficiently solvable just by directly applying some algebraic methods like Grobner-Basis. However, in our paper, we showed that using the elimination ideal technique and a set of variable transformations and clever reparameterizations, we can significantly simplify these equations and transform them into a very simple univariate polynomial of degree 3 or 5, or a simple system of 2 equations in 2 unknowns. So in our paper, we propose several efficient solvers that cover all possible configurations of cameras and points. These solvers efficiently solve a univariate polynomial using Sturm sequences, and their running times are few tens of microseconds compared to a few milliseconds of general solvers. We tested these solvers in a localization pipeline, and we showed that the proposed solvers are faster while achieving comparable accuracy to that of the general solvers, even in the presence of non-planar scenes. I think Torsten will show maybe some results in his part. So in conclusion, this part of the tutorial covered the camera pose solvers, especially absolute camera pose estimation problem, which is an essential part of many of the localization pipelines discussed in this tutorial. We have covered highly efficient solvers for calibrated cameras. For partial calibrated cameras, the underlying system of polynomial equations is more complex. Still, recent progress in developing minimal solvers leads to highly efficient solutions even for rolling shutter cameras, and the running times of most of these solvers is few tens of microseconds. Interestingly, many of these advanced solvers are not widely used. This is probably due to early solvers being rather inefficient and not yet ready for practical applications. And further, some of the solvers are hidden in papers, focusing, for example, on improving the efficiency of minimal solvers or some general algebraic methods for solving systems of polynomial equations. So maybe they are not so known. Note that non-minimal solvers, especially minimal plus one solvers, can sometimes be much more efficient than minimal solvers, and thus be preferable in practice. So sometimes it may be better to look also at minimal plus one solvers. On a final note, I want to point you to POSLib library as a starting point for finding efficient implementations of minimal solvers, some solvers that I presented in this talk. So thank you very much for your attention, and I'm happy to answer questions. I think maybe we don't have time to answer it live, but I can answer them in YouTube chat.
Thank you, Susanna, for the presentation. Let's remind people, that they can post their questions in the chat, and you can maybe even take some questions afterwards.
Yeah, sure.
Okay, good. Torsten, maybe you can get prepared by sharing your screen.
Okay, good. Can you see my screen?
Yep, looks good.
Perfect. Okay, so let's welcome to the second part of this tutorial. So Susanna just talked about how to estimate camera poses from a set of correspondences. And in my part, I'm actually essentially going to talk about how to get these correspondences for camera pose estimation. And I'm going to focus on feature-based methods. And these, while seeming potentially outdated a bit, are still widely used in practice. So on the left, you see an application that, like a demo that we probably showed at ICCV 2014, where we use localization in an augmented reality setting. So we localize the camera, and then based on the pose of the camera, we're able to display virtual content into the view of the user. And on the right, you see a similar thing made available, or that's part of Google Maps on Android devices, where you can lift the camera, and it figures out where you are in the world, and then gives you navigation instructions. And while I'm not 100% sure whether they use feature-based features, it looks to me like, given the animation that you saw before, where let me find it, where it actually showed a couple of features popping up. So it seems like it is using features. Another use case is performance capture. This is from a paper that we published at CVPR this year, where we are combining a head-mounted camera for localization with body-mounted sensors to not only get the position of the user in the scene, but to also get information about the position of the limbs, the human body pose, which I believe is a necessary step towards having interactive application, interactive augmented reality, interactive virtual reality, where you need to know the human body pose in the scene in order to be able to interact with virtual objects in a physically plausible manner. Taking a step back, so we can look at, this is an attempt at providing a taxonomy for visualization algorithms. I'm going to split it into two halves. The first one is image-based representations, with the simplest one being image retrieval. So you end up with a set of cameras, each one having a camera pose. You have a new image, and you try to identify what's the most visible, most similar database image, and approximate the pose of the test image through the pose of that database image. You can do slightly better by not just taking the nearest neighbor, but doing some form of interpolation among the top retrieved images. So you essentially try to compute a weighted combination of the poses of the top retrieved images in the hope that this will give you a more more accurate approximation. There are approaches that train a CNN to take an image as input and then predict an output pose. But as Eric will detail later in the tutorial, many of these approaches are rather approximate in nature and typically not that much better than pose interpolation or image retrieval. But you can use image-based representations for accurate pose estimations. One way is to do pose triangulation. So you have the query image, you compute relative poses between the query and the top retrieved images. And then for each relative pose, you know that the query image somewhere has to lie along the direction of translation. That's essentially a triangulation problem. And then you can use triangulation to compute the position from which the query was taken. You can, of course, either do this with relative pose solvers, or you can train a network to directly regress the relative pose between two images, either with a known scale of the translation or without a known scale. And as Susanna just mentioned, rather than estimating individual relative poses, you can estimate the relative pose between a pinhole camera and a generalized camera, and then get the translation scale on top of this. And this can be done either in the general setting or in the setting where your scene is planar. The second set of methods are 3D structure-based methods. So they represent the scene through the 3D geometry of the scene, either explicitly, for example, as a set of sparse 3D points, where each point is associated with a local feature. And if you have a new image, you can extract local features, match them against the features of the points, get 2D, 3D matches and do pose estimation. Or at the other end of the spectrum, you can implicitly define, represent the scene geometry through the weights of a neural network or the split nodes of a random forest. And then rather than explicitly matching features, you run your image through a CNN, get a corresponding 3D point for each pixel, and that also gives you 2D, 3D correspondences. Somewhere in between is pose refinement, where the idea is that you have some initial pose estimate. You can project 3D points visible from this pose estimate into your query image. You compare the projections against the actual image, and then use this comparison to refine your pose estimate. Of course, this taxonomy here suggests like a binary split, but it's actually more of a gray zone somewhere in between, because you can have hybrid approaches. So for example, hierarchical localization approaches first do image retrieval and then do feature matching only against the points visible in the retrieved images, which cuts down matching times. Or you can do pose estimation based on a mixture of 2D, 3D and 2D, 2D matches. The image retrieval part is what Yorgos talked about. I'm going to talk about these things, so feature-based localization, some hybrid methods, and the accurate image-based representation localization methods. And Eric is later going to talk about the scene coordinate and camera pose regression parts. Structure-wise, I'm going to talk about, start with feature-based localization. This is where I'm going to spend most of the time. Then I will talk briefly about hierarchical localization, similarly briefly about methods that are based on image-based representations rather than structure-based representations. So let's start with feature-based methods. This is what I would call old school localization. So you have some sparse 3D model or some 3D model of the scene. You have a test image. You do feature detection and feature description. So for example, you run SIFT on the image. And then you match the descriptors that you extract from the image against descriptors associated with 3D points, get a set of 2D, 3D matches, and you do pose estimation inside RANSAC using one of the endpoint pose solvers that Susanna just described. And I call this old school localization because like the feature detection description part, so the most popular one is used to be popular is SIFT, which was developed first published in 1999, but was developed earlier, and there were earlier feature detectors and descriptors. Descriptor matching, like one way to make this efficient is to use KD trees, which were developed in the 70s, and they're probably spatial acceleration structures dating before this. And then, as Susanna pointed out, we had P3P solvers in this 18th century, and RANSAC is by now nearly, is exactly 4 decades old. And there are early examples of those pipelines if you want to look a bit into history. But the question is whether this isn't outdated and we should just move on and not discuss this. My argument is that it's not outdated. So if you compare those old school methods against what I would call the new school, which is methods that rely on machine learning to do the 2D, 3D matching stage, then you see that outdoors feature-based methods hold their own quite well. So here you see results on 2 data sets, Cambridge landmarks, where we show the average median position error, so smaller is better. And you see that feature-based methods, those are the green bars, are able to outperform methods that use the CNN to establish 2D, 3D matches. Similarly, on the Aachen data set, where we show the percentage of images localized within 25 centimeters and 2 degrees, we see that feature-based methods currently outperform the scene coordinate regression based techniques. This is one snapshot. Eric will tell you more about why you should not necessarily take those values. You should not draw absolute conclusions that one method is better than the other, because it depends a lot on the way the ground truth is generated. But it shows that like these old school localization techniques are still relevant. Okay, so let's look at 1 or 2 examples for feature-based localization pipelines. I'm not going to talk about feature detection and description. That's like a whole lot tutorial for itself. I'm going to talk a bit about the descriptor matching stage, and Susanna already talked about camera pose estimation. So 2D, 3D matching essentially assumes that you have some 3D model of the scene. This can be reconstructed using structural motion. So here you see part of the Aachen 3D model. Here each colored point is one of the structural motion 3D points. Each red thing here corresponds to one of the images used to reconstruct the scene. And each 3D point was triangulated from at least 2 images. So meaning you can associate each 3D point with a spatial coordinate and the descriptors of the features that were used to generate this 3D point. If you have a new image, you can then compare descriptors. So you essentially descriptor matching or 2D, 3D matching is a nearest neighbor search problem, where you would like to find nearest neighbors in the descriptor space. And typically this is done approximately because your descriptors are high dimensional and you can't have anything faster than like exhaustive search in high dimensional spaces unless you do approximate search. One popular approach is similar to what people have been doing in the retrieval literature. It's based on inverted files. So the idea is you quantize your descriptor space, and for each cell, you store a list of descriptors that fall into it. And if you have a query descriptor, you figure out what's its corresponding cell, compare it against all descriptors stored in that cell, and potentially also visit a couple of other cells nearby. This is linear time complexity still, but you typically have a small constant, and the advantage is that you have cache efficiency because you can cache the descriptors in one cell. And there are very good software libraries to do nearest neighbor search for you. One is the FLAN library by Muya and Lowy, and the other one is Facebook's FACE library, which I can very much recommend. Both have open source code. Both are well documented. So let's look at the simple baseline. The idea is we have our 3D model. We represent each 3D point by the average descriptor among all descriptors associated with it. And then we build one KD tree that contains all descriptors. If you have a test image, you're just for each feature, you're going to traverse the tree, looking at a couple of leaf nodes and then find the 2 nearest neighbors. And then you apply Loewy's ratio test, which essentially is the distance of your query feature to the nearest neighbor divided by the distance to the second nearest neighbor. If the second nearest neighbor has a similar distance, then this ratio is close to 1. And it essentially means you don't know which of the nearest neighbors is the correct one. If you have a small ratio, then that means the nearest neighbor is much closer than the second nearest neighbor. And then you do pose estimation. And in the end, you have to select whether the pose is valid or not. And this you typically do by looking at the number of inliers that you get. 12 seems to be a nice number. And this is a pipeline that works well, but can be slow in practice. But luckily, there's actually quite some room for improvement, which is based on the observation that you do not necessarily need all the matches that you can get for accurate pose estimation. And one approach that works well is a very simple greedy strategy for prioritized matching. So the idea is that for each feature that you have, you try to figure out how much time do I need to spend to find a match for it. And this you can do easily. So let's assume that this is your descriptor space. These are your query features. You simply quantize the descriptor space. You figure out for each feature in which cell does it fall. And then you know that in order to evaluate the purple feature, you would need to compare it against 3 descriptors. Same for the green one. The blue one would only need 2 comparisons, and the red one would need 5. So you can start with the features that are easy to evaluate. So you would start with the blue one, then do the green and the purple one, and end up with the red one. And you stop the matching procedure once you have found enough matches. So this is a simple approach. It has a nice semantic meaning. So parts of the descriptor space that contain less descriptors mean that these descriptors are globally more unique, where parts which contain more descriptors mean that like the physical structure that's corresponding to those descriptors is more ambiguous. And this is actually similar to the classical IDF weighting used in the retrieval literature. And you can use this for a simple vocabulary-based prioritized search scheme. You have your quantization in, say, 100,000 words. You first assign all features to the closest word. That gives you a list of search costs for each feature. You sort the features based on costs, and then you go through this. You do a linear search through each word. So for the orange feature, you find the 2 nearest neighbors. You apply the ratio test. Both have a similar distance. You don't get a match. For the red one, you see that the nearest neighbor is sufficiently closer than the second nearest neighbor. You get a match, and so on. You stop after finding, say, 100 matches and run the pose estimation. That's significantly faster than KD tree-based search, but also doesn't work as well. And the reason is that you have quantization artifacts. So in this case, for example, the green query feature is assigned to a different cell as the corresponding 3 point, meaning you will miss that match. And there's a simple way to recover this type of matches that adds very little computational effort. So the idea is that you can exploit the co-occurrences of matches. So let's assume that you have been able to match the purple query feature to the purple 3D point. And you know that if this match is correct, some of the nearby 3D points of the purple point should also be visible in your query image. Meaning you can take these and match them back against the image. And this can be easily integrated in this vocabulary-based prioritized search scheme that I discussed, because initially you would assign each feature to a visual word by traversing some form of tree. And if you use a vocabulary tree, meaning each level in the tree is a quantization of a different level of detail, you can actually stop somewhere pause somewhere along the tree and say, in this coarser quantization, I'm falling into this cell. So you get this for free because you need this assignment anyways. If you want to match the green point, you just walk back the hierarchy a bit, figure out where it falls in this coarser level, and then you can match this green point against all query features falling in the same cell. You do the ratio test and you get matches. And so this really helps to reduce quantization artifacts. You don't need an additional data structure, search structure, and you can actually prioritize over 2D, 3D, and 3D, 2D matching because it's the same type of thing. You look at the number of descriptors assigned to some visual word. So that gives you similar performance as KD trees at faster runtimes, but it's still a bit slower than like the vocabulary-based prioritized search scheme. But you can reduce some of the operations that you do using taking visibility into account. So there's a concept of the visibility graph, which is a bipartite graph, where one set of nodes correspond to 3D points in the reconstruction. The other set of nodes correspond to the images that we use to reconstruct these points. And you have an edge between a point and a camera if that camera observes this point. And you can use this for visibility filtering. So let's assume that you want to match, you found a match with the red 3D point, you find nearest neighbors in 3D that you want to match back against the image. And you can essentially try to, in this case, you would know that it doesn't make sense to match those two points because they're not visible. And you can get this information from the visibility graph, because if these points are not visible together with the red point, then there's no camera that jointly observes them. And this allows you to essentially filter out these 3D points before you do the backmatching step. Similarly, once you have a set of 2D, 3D matches and want to run ransack, you can essentially try to find, like this, the matches define a set of connected components in your visibility graph, and you can only keep the matches in the largest connected component. Both can significantly accelerate things and are very much recommended. So this is an approach that I actually worked on during my PhD. The interesting thing is that the original paper was published at ICCV 2012. So the method is nearly 10 years old. The core of the method is nearly 10 years old. But if you look at recent examples, then it actually still performs very well on data sets where there are no large condition changes. So say you have all your images taken a day, then this method will still work very well. And Eric will talk a bit about this method called active search with respect to scene coordinate regressors later. So the takeaways about this part is that feature-based methods, even when they use SIFT, are still rather competitive. And they actually currently give you state-of-the-art on medium and large-scale datasets. Prioritization is a nice thing if you want to do things fast. So you try to look for unique structures and try to find matches for these first. And visibility filtering is definitely something that I recommend doing. We will later see that you can also use it for hierarchical approaches. There's a lot of literature on this. So these are ideas that were presented around 2010, 2012. If you want to know more, please look at these references. I will make the slides available on the website later. But scaling to larger scenes or more complex scenes with these type of methods is challenging. So let's look at a reasonably sized scene. This is your query image. Then most likely you will have like a unique match for features where you can get a match. Meaning the ratio test will tell you, oh, my nearest neighbor is much closer than the second nearest neighbor, and you will get a match. If you look at larger scenes, say partially city scale, then there's a good chance that there will be other structures that with like a similar visual appearance, meaning your descriptor space becomes much denser and the ratio test starts rejecting wrong matches. So you are in some sort of chicken egg problem. You can't have too many wrong matches, otherwise your ransack time becomes too long. But you can't also have you also have to find a certain number of correct matches, otherwise you will not get a good post estimate. And the challenge here, as I said, is that the central assumption of a lot of early feature-based methods is that you can use the ratio test to identify correct matches. This is especially true for prioritized search methods. You can recover some of the matches with active search, but you again need to find some additional, some correct matches to begin with, and this becomes increasingly harder at scale. One way to address this is to not use ransack directly, but to use voting schemes that scale better with the number of matches. So here you see one example. This is the query image. This is the whole voting map for the whole scene. This is zoom in. Dark blue means, dark blue / purple means there are no votes. Red means a lot of votes. And as you can see, we get like a rather clear peak for the position from which the image was taken. The way that these approaches work, and I'm not going to go into technical details here, is that assuming that you know the gravity of direction, which you can get from an IMU, or in this case also from vanishing points, if you fix the height of the camera and the orientation of the camera, then you get, then each 2D, 3D match that you have will vote for a clear position in the world. And typically you get like a good estimate of the height of the camera, because in many applications, it's like maybe 2 meters, up to 2 meters above the ground. And you can simply iterate over different orientations, because once you know the gravity direction, there's only one angle that you need to iterate over. And then you can do voting for each of these combinations and get the full pose. And the nice thing is that this is linear in the number of matches. So it actually scales rather well. You can have a lot of outliers without like a combinatorial explosion in your runtime. Another nice thing is that you naturally get uncertainty estimates. So this is an image that was taken rather far away from the scene. Most of the matches are a few, like tens or hundreds of meters away, meaning your camera pose is not that well constrained, and this is reflected in the uncertainty estimate. So you probably have like multiple meters of uncertainty in the pose estimate. And you can naturally handle challenging scenes such as this building, where both one side and the other side look like nearly identical, and like visually, without looking into fine details, both poses seem plausible. There was an interesting paper at ICCV this year where they show that this can be also generalized into the case where the intrinsics of the camera are not known. And they show that under certain conditions, this at certain points, this is much faster than ransack. Another approach, which is partially orthogonal to this, is to subdivide your scene into many small parts, say 150 by 150 meter tiles, and then using some sort of prior, for example, GPS or Wi-Fi node ID, you can figure out in which cell you fall. And then you only do matching and pose estimation within this tile. Can in addition also try to like compress the structure to avoid memory, like explosion in memory. But this works is something that how you can do a scalable localization in practice. So the takeaways here are, if you want to scale things, then one of the main challenges that you will run into is that all of a sudden multiple things in different parts of the scene will start looking very similar, and you will have problems disambiguating between those views. And as I said, there's a trade-off between filtering out too many correct matches and not being able to get a pose estimate, or having to pay the price of handling a large number of outliers. Voting here helps you with large outlier ratios and can provide you uncertainty estimates. But it can be quite slow to implement because while it's linear, the constant in this linear runtime can be quite large. If you can simplify the matching problem, for example, using some post price, then that typically helps you avoid many of these similar structure issues that you encounter at scale. There's a large literature on large-scale localization if you want to have a look at this. Talking about scalability, you can also look at scalability to mobile devices in the sense of you now all of a sudden have to deal with limited compute, limited storage, and energy consumption becomes an issue. At the same time, you need to do localization real time for applications such as augmented and virtual reality. The key idea to do localization here is that our key insight is that most likely you will not be able to do localization from scratch in every frame, but you also don't have to. So you can localize every now and then, and in the meantime, use SLAM or visual odometry to track your camera motion locally. And the idea is that global localization essentially prevents a local camera pose tracking from drifting away, as essentially always snaps it back against the map. It's essentially doing some sort of loop closure, while the local tracking allows to run things in real time. So the idea is you do tracking, for example, by SLAM, you build like a small fixed size local model that you use to track the camera pose. Once you get a new keyframe, meaning you would be extending the model or changing the model, you try to localize this with respect to some global model. You get a pose, and then you try to incorporate the global localization results into the local tracking to prevent drift. And this can be done either by saying, okay, this is the global position or global pose that I get. My local pose should be nearly identical. Or you can do this by taking the 2D, 3D matches that were used to get the global pose and adding them as constraints in the form of reprojection errors, saying that these 3D points should project close to the corresponding observations. The latter, in our experience, works better than taking the pose estimates that you get directly. Here is one example. So this is the red is the ground truth trajectory. Blue is the trajectory that you get if you essentially use position constraints to prevent drift. And the green one, which is closer to the ground truth, especially in this part here, essentially uses these constraints based on 2D, 3D matches in minimizing a reprojection error. The reason why this doesn't work here well is that here the camera goes around a corner, and now all of a sudden all of the geometry that you see is far apart, meaning your camera poses have a rather large uncertainty. So you could shift the pose by a meter probably and still get similar reprojections in the global localization scheme. So and if you just then take these rather uncertain camera position estimates for face value, you will have jumps, whereas the method based on reprojection errors handles this gracefully. So coming back to the mobile localization system, you have limited computational power and memory capabilities, and decoupling like global localization and real-time post tracking doesn't solve this problem at all. You can here either use client-server architecture, where you send images to the server in the form, for example, of an AR cloud, which does the heavy lifting for you, the global localization, which allows you to really limit the memory footprint and processing power on the mobile device. Or you can also try to compress your global map so that it fits onto a mobile device, or you can potentially also do both. Map compression, I'm not going to go into details here. The basic idea is that you don't need all 3D points that you have in the model to do accurate pose estimation, but you can use a subset of them. And especially if you are combining this with local camera tracking, where you really don't need to localize every frame, you can actually use a rather small fraction of all original descriptors of 3D points. So what you see here is the fraction of original descriptors, 3D points, that are used in the local map. This is the position error as a function of this descriptor count. This is the absolute pose recall, meaning how many frames can I localize. And naturally, as you compress your map, you can localize fewer frames, but your localization errors remains approximately the same because you do local tracking in between. Whether you get global poses every 10 frames or 100 frames doesn't really matter that much, as long as there's not too much drift. And that means you can go from easily from 140 megabytes for the full model to 20 megabytes without any noticeable degradation. So this is an example. On the left, you see 35% of the original data points. On the right, you see 5% back projected into the image. And there is very little difference in terms of pose accuracy between the two of them. You can further compress your maps by compressing your descriptors, for example, using product quantization. Yannis did some work on this at CVPR 14 and later. And if you do this, you can actually, this is the position error as a function of the model size, orientation error. And as you can see, you can get away with 4 megabytes or less for a map that spans about a kilometer in trajectory without seeing too much, too large a drop in performance. So the takeaways to the mobile localization things here is that the key idea is that you combine global localization, which you do at a low frame rate, but where you don't have like global drift, with camera pose tracking that you can run at a high frame rate, even though it has drift, and the global localization that prevents you from accumulating this drift. Matte compression is necessary if you want to run it on mobile devices, but also if you want to have an architecture that scales to thousands of users, because you potentially need to read maps from disk. The smaller they are, the faster you can read them. And map compression consists of two stages: structure compression and appearance compression. And again, there's a larger literature on this if you're interested. Let's have a quick look at hybrid localization. So the idea is that rather than only looking at features, you exploit the fact that you used images to reconstruct your 3D model in the first place. Then you can use image retrieval to, for a given query image, figure out that this image, database image, is the most similar one. And you do 2D matching between the query and the retrieved image. You know which features in the retrieved image correspond to 3D points. That gives you a set of 2D, 3D matches. And then you can do pose estimation. And you essentially exploit that the retrieval step allows you to restrict 2D, 3D matching to a subpart of the 3D model. And as part of that, avoid these global ambiguities that I talked about before. And as a historical side note, people have been doing this for quite some time. So there was a paper at CVPR 2009 which showed that you can implement such a pipeline in real time on 2009 hardware or even older hardware. State-of-the-art localization systems still follow the same thing. They take database images, compute local features and global features, build indices, use local features for structure from motion reconstruction. And in the online phase for a query image, they compute a global descriptor, do nearest neighbor search, figure out which of the database images are relevant, do 2D matching, get 2D, 3D matches, do pose estimation. One example here is Paul Edward Saulin's work on this, which has very nice implementation online. One of the tricks that he uses is assuming that these are the retrieved images and the 3D points visible in them. He uses this visibility graph to cluster them. So rather than running pose estimation for the matches found with this camera and this one, runs matches for all images in for all matches found in one connected component and for all images found in another connected component. as a nice side benefit, you can get multiple poses, which is nice if you have ambiguous structures. And current, as I said, current state-of-the-art methods use are based on hierarchical methods using learned global descriptors, learned local features, and learned feature matches. If you're interested in playing around with this, there are good implementations in the HLOC pipeline and the capture pipeline by Naver. As a side note, these hierarchical methods also seem to work well under changing conditions. Say you have database images taken at day and you query images taken at night. And the reason why this works is that you only need to do local matching, not globally. If you want to know more about this, you can have a look at the results of visual localization document. Okay, let's come to the last part, which is about image-based representations. So the question here is, are large scale or 3D models in general really necessary? The reason for asking this is that maintaining 3D models is hard. So if the scene changes, you need to add images, remove them, then you also need to add and remove points and update your index search structures. Similarly, if you want to switch to a new and better local feature type, you need to rematch and retriangulate, which can take some time. So the question is, do we really need this? The answer is that you don't need this. You can do structure-less localization, where you only store images and their known poses, but no 3D parts. So this is easy to update. You just add or remove an image and its pose from a database. You don't need to rematch or anything. And you can extract features on the fly. So if you want to switch to a newer feature type, nothing is going to prevent you from this. And the way that those pipelines work is you have a query image, you do image retrieval to identify the most relevant database images, and then you estimate relative poses. And together with the known pose of the retrieved images, you get the absolute pose. I mentioned this at the beginning of the talk. You can do this either by estimating the relative pose of the relative pose of the query with respect to each of the retrieved images, and then then triangulating the camera pose. You can do this both for calibrated camera queries, but also for uncalibrated queries, where you can use Susanna's work to estimate the relative pose between a partial calibrated camera and a calibrated camera. Then the other thing is to model all of the retrieved images as a generalized camera with known relative poses, and then use a semi-generalized tomography or semi-generalized relative pose solver to get the pose of the query with respect to that generalized camera, in which case you actually can observe the scale of the translation. Last thing that you can do is you could also build a structure for motion model on the fly. So you take the retrieved images, you do feature matching in between them, triangulate the 3D structure, and then can do pose estimation with an absolute pose solver. You can do also hybrid things. So you could use both 2D, 3D and 2D, 2D matches for pose estimation. But I'm not going to go into details for the sake of the length of the tutorial. There's a couple of further topics that I'm also not going to talk about, but you might be interested about them. One is to use semantics, either to build descriptors, to verify matches, or to directly do localization based on objects rather than general scene 3D structure. Another thing is domain adaptation in the form of image translation, say between day and night images, or between renderings and real images, to have a better, make feature matching easier. And that concludes my part. Thank you very much for your attention. And the next part is Sudipta talking about privacy preserving visual localization. And I'm happy to take or to answer questions on YouTube. Thank you very much.
Right. Hello. Can everybody hear me?
Yes.
Okay, I'm going to share my screen, and then let me know if you're able to see my screen and my presentation. Just a moment. Swap. Do you see full screen?
Currently not, no. I only see you.
Okay, so the Zoom. Oh, so I have to permit. Okay, there we go. I have one more button to click. So there we go. And start this presentation again. Should be good now, right?
That works. Thank you very much.
Thanks, Carson. So yes, so welcome everybody to the next part of the tutorial. I'm going to do a brief recap of this topic of privacy preserving camera localization, which is relatively recent, I would say, subtopic within this broader field that the tutorial covers. And the main motivation for looking into this specific subtopic is that visual localization is becoming sort of a fundamental piece of a lot of technology that is maturing and is getting sort of deployed in the real world. So this is primarily due to advances in mixed reality, augmented reality that is happening at several companies, as well as a lot of deployment of robots in our homes and workplaces. And so as this trend is going to continue, there are lots of sort of new questions that come up. And so my part of the tutorial is going to talk about, basically try to answer these questions. What are the privacy implications of having these localization systems deployed at scale? What are some new challenges that brings up if you want to address them? What solutions have been developed so far, and to what extent are they effective? And I will try to give some pointers to lots of new open questions that still haven't been addressed. So the basic setup follows exactly from what Susanna and Thorsten have talked about in the last 1 hour. This is, I'm going to basically pose everything in the framework of what Thorsten was referring to as old school localization. So the input to these algorithms are query images. I'm going to always assume that a pre-computed map is reconstructed. This map is basically the 3D point cloud where points have associated descriptors. All this computation is being done a priori. And so the privacy, and so I'm going to now basically bring this additional goal of saying, in addition to doing camera localization, there are going to be some additional goals that we want to address. And that's where the privacy aspect comes in. So, and as I do that, I want to point out to this work from 2 years ago, where we did a project where we took structure for motion point clouds. We took the kind of data that is used by the localization systems, and we showed results. We kind of systematically analyzed these representations and showed that it is possible to take these camera localization data sets and invert the point clouds and descriptors to produce very detailed and realistic images of the scene. Even though no images were being stored by these systems, it's basically possible to recover very detailed images of the scene just by using neural networks to invert the feature data, the feature descriptors that are being stored. So here's an example. On the left side, you see the input to this neural network is a bunch of sparse feature points. So these are, like, if you take the point cloud and you project it into a certain viewpoint, you would get an input as shown on the left side. And so for each of those colored pixels, you have a associated descriptor. When you pass it through through a neural network, which in our case consists of 3 units in series, you get this RGB image that can be reconstructed. And we were able to train this neural network on large, public internet photo data sets. These nets do a pretty good job of generalizing to new scenes. And so the upshot is that an attacker could use this kind of a method to recover visual imagery of a scene. And if the scene was confidential or the scene contained sensitive content, then a method like this could basically be used to sort of compromise privacy of the users. So here are some visual examples shown on the top row are the input to the neural networks. It kind of shows you that even for very sparse scenes, the inversion still works pretty well. The middle row shows the results of the inversion attack, and the bottom row shows what the actual images were. And this is another result, visual qualitative result, showing that you can sort of reconstruct the full video, one of the videos of a scene that was used to build the map. So the implications of this work was that we wanted to explore essentially this new task, which we called privacy preserving camera localization. And there are primarily two different scenarios where this work becomes important. And in these two scenarios, the goals are also slightly different. So shown on the left side is the first scenario where you have a localization system where all the computation runs on the client. So in such a system, the map that is built a priori would be shared out to the clients. And in this scenario, what we want to achieve is we want to conceal the map data in some way so that this kind of inversion attack is not possible. On the right side is shown a second scenario, which we refer to informally as cloud-based localization. This is the more common scenario which is being used nowadays, where you could imagine lots of devices connected to the cloud. And these devices would essentially take an image, and these images would be processed and features would be extracted and uploaded to the cloud service. And all the computation would run inside the cloud service. So in this scenario shown on the right, what becomes important is to basically conceal the image features of the query image features. And because in this case, the map data remains on the cloud, remains confidential. What you want to now do is kind of conceal basically prevent the inversion attack from being run on the features of the query image. So to make things a little bit more concrete, here sort of like restating what I just said. So there are these sort of two scenarios, and the new privacy preserving camera localization tasks, which are being explored in these new papers, have these specific goals. So in addition to computing the camera pose accurately, we want to successfully address the second goal. So in the shared map scenario, we want to prevent an attacker from reconstructing images of the scene by inverting map features. And in the cloud-based localization scenario, we want to do the same, but prevent the reconstruction of the query image appearance. And what is shown on the slide is some results of work that has been done in the last couple of years in the domain of like reconstructing, doing privacy preservation of map data. The first work that appeared was by Speciale et al. In 2019, where a new method for camera localization was proposed. It used a new data representation called 3D line clouds. But earlier this year, there was a paper by Celani, Carl, and Sattler, interestingly, they analyzed the method proposed by Speciale et al. And showed that the privacy claims were not guaranteed to be satisfied. And their main takeaway, their main insight was that they showed convincingly that just using line clouds alone is not enough, and more needs to be done. So this space is basically at the moment, there is no method, there's no satisfactory solution that exists yet. And definitely there's a scope to do a lot of interesting work in this domain. Then on the cloud localization scenario, which is the other scenario that I talked about, where images are uploaded to the cloud, there were mainly two works I'm going to briefly touch upon, which appeared in the last 2 years. And in these cases, the data representation is changed by taking the image features. In the first case, the feature points are transformed into feature lines. And in the other paper, the feature descriptors are modified. So I'll briefly touch upon this in the coming slides. So this was the paper by Speciale et al. So I'm going to briefly talk about the idea they proposed of 3D line clouds. So this cartoon diagram shows the basic idea. So shown on the left is an image which is supposed to represent a 3D point cloud. These points are they're going to have associated descriptors, but that's not shown here. The idea of generating a 3D line cloud is simply that for each 3D point in the point cloud, you would pick a randomly oriented 3D line. So essentially, you would pick a random 3D direction, construct the 3D line that passes through the point, and then discard the point. So the image shown on the right side is a visualization of a 3D point cloud. These lines are all in 3D, so they don't necessarily intersect. And then the idea about this paper was to use this 3D line cloud to do camera pose estimation. So before talking about that, here's what that 3D line cloud could look like. Shown on the left side is the original 3D point, and on the right is the 3D line cloud. So the core idea of this paper was that when you do traditional pose estimation with point-to-point correspondences, each image to 3D point correspondence gives you 2 constraints. And therefore, in the minimal case, you need 3 point correspondences to solve for the pose. However, when line clouds were proposed, the basic idea was that you take away 1 degree of freedom from every 3D point. And so now you're left with a single constraint. So if you have an image point denoted by a small x and a 3D line denoted by capital L, then the geometric constraint that you can still enforce is that the ray back projected from that image pixel should pass through, should intersect the 3D line somewhere. So now each correspondence between a point and a line would give you 1 equation, and you need 6 equations to solve for the 6-dot camera pose. And this is the core idea of this line cloud based pose estimation paper. And what is interesting was that the paper didn't necessarily propose a new algorithm for pose estimation. Rather, what it showed was that the line cloud based pose estimation is nothing but it can be cast into the generalized relative pose problem and other generalized pose estimation problems that have already been proposed in the literature. So the implementation of the idea was basically done by reusing existing solvers. So earlier this year, this is a paper by Kunal, Frederick, and Torsten, where they analyzed this method and they looked deeper into it, and what they found was that the original claims of Speciale et al. That this transformation of the data ensures privacy was not necessarily true. What they showed counterexamples. They basically proposed a method where they showed that the 3D line cloud could be inverted back. You could basically recover the original point cloud approximately using a geometric algorithm. And by doing so, they were able to show that you can still apply the original deep neural network based image recovery technique and recover images of the scene. And the main insight of the paper was that when 3D line directions were being chosen uniformly at random to create the 3D line cloud, the position of 2 closest points between a pair of 3D lines gives you a good hint about where the original 3D points lie on those lines. And this is especially true when those 3D points are near each other. So this core geometric intuition was shown to be the basic. This is the basic intuition for the algorithm, which basically has this notion of it's an iterative method, but there are sort of 2 basic steps. One is the method tries to find neighborhoods of points for each unknown 3D point or line by doing some local geometric analysis. And then there is some robust peak finding to basically find a single 3D candidate per line. And when you do this multiple iterations, they showed very convincing results that in many cases, the line clouds could indeed be inverted. So switching gears to now the other side of the whole picture, which is doing localization in the cloud. To remind you that in this scenario, and this is particularly like something that Microsoft, Google, and others working in the augmented reality space are interested in. So we have devices that connect with the cloud, and the map stays in the cloud. But in this case, the query image is the one that is processed, and information of features extracted from the query image would be uploaded to the cloud. And so the privacy preserving localization goals are that we definitely want the camera pose to be computed from the image features, but we want to prevent a malicious attacker from inverting the features on the server, or it could also be a man-in-the-middle attacker. And to address this goal, Special et al., we basically, in a follow-up paper in 2019, looked at this problem and extended the 3D line cloud idea to this particular problem setting, where given image feature points, we do a very similar transformation. In this case, we select a random 2D direction on the image plane, and then we construct a randomly oriented 2D line passing through each original 2D key point. Once we do that, we discard the original 2D point. And so now we are left with a 2D feature line for each key point and the associated descriptor. This is the information that is uploaded to the cloud. And then we're going to do both estimation based on that. So just like in the previous case, we have given up one of the constraints that you would have if you had a point-to-point correspondence. What is interesting is that now we have a line in the image. And so if you back project this line, what you get is a 3D plane. And the constraint that we can still enforce is that the 3D point in the map must lie somewhere on this 3D plane. So again, this is not a completely new problem. This has been studied in the literature. This is the point-to-plane problem. Ramalingam et al. Investigated minimal solvers for these problems, but in different scenarios. So the paper basically investigates the variance of this point-to-plane problem where other information is available, such as when you have the knowledge of gravity, or for some reason you may know the scale of the map. And so what the paper shows is that in all these cases, the feature line-based camera pose estimation methods, they're able to recover pose pretty efficiently and pretty accurately without having a lot of computational overhead. So here's a visualization showing what sort of information gets revealed after pose estimation. So in this particular case, the query image contained a person. This is a person who was only photographed in this particular image. And when the features are uploaded to the cloud by a traditional method, and if you ran that inversion attack, you could now reconstruct the appearance of the whole image, including the appearance of the person in the photograph. Whereas on the right is showing the result that you would get if you ran the inversion attack on features that are essentially in places where you get inliers in the image. So the basic idea is that any transient object, such as a person in the photograph, even if you had local feature descriptors extracted around those locations, these features would never be matched to the map. Therefore, you would never be able to recover the true location of the 2D points for these transient features, objects. Whereas for the inlier points, the pose estimation would actually reveal the true 2D location of the descriptors. But what is nice is that in some cases, these transient objects are exactly what we want to conceal, and the method seems to do a reasonable job at that. So quickly before I end, there is another work I wanted to mention here in this paper from CVPR 2021. What we looked at was, what if we didn't actually modify the key points, like in the previous paper that I talked about. Instead, what if we tried to conceal the descriptors? And the core idea here was to apply a transformation to the feature descriptors by embedding them into an affine subspace. And then the paper looks at a way of doing matching between subspaces to get the correspondences. So I'd like to wrap up my section. So in summary, I have talked about a new sort of problem or a new task that we have defined, where we're interested in localizing cameras accurately within maps. But in addition, we would also like to address certain privacy goals. And primarily, we've looked at concealing the appearance of the maps or concealing the appearance of the query images by basically trying to incorporate different geometric constraints into the problem. In particular, the map-based, the privacy preservation of maps, it's still an open problem because the original problem of the line cloud-based method was shown not to work well in many cases. And on that line, there's sort of some work that is being explored by others in the community. There's been some work trying extending the ideas to SFM and SLAM, but there are a lot of interesting questions in particular, like, are there better ways to construct 3D line cloud maps that don't have the weakness pointed out by Chelani et al.? And what sort of role does what sort of like we still haven't looked at any of these learned localization approaches, and it's very interesting to ask, what sort of privacy concerns do they address? Is there more work needed in that area? And with that, I would like to end my section of the tutorial, and we can address questions in the chat later. Right. Great. You're next.
Yes. So first, I have to figure out all the screens that I have and that I share the right ones, the right content.
We hear you and see you, and yeah, we see the full screen now. Looks good.
Great. So to check my setup, that everything is all right. Okay, hello everyone. I'm Eric. Welcome to the third part of the tutorial covering learning-based methods for visual relocalization. I'm a senior research scientist at Niantic. Here's some information if you want to reach out after the talk. And I want to start the talk with a brief history of Niantic, actually, because I think most people see Niantic as a gaming company, Pokemon Go, Ingress, and so on. But actually, it's also a mapping company. So it started as Keyhole in 2001. A company which was acquired by Google and became Google Earth and Google Maps. And the founders of Keyhole, they then started this company, Niantic Labs, within Google, which then became the standalone Niantic in 2015. 2016 was the summer of Pokemon Go. And then today, Niantic wants to re-emphasize that actually it's a AR tech company. So it's not only creating games, it's also making technology available to create these games and these AR experiences. So in its origin, Niantic has basically always been a mapping company. So it makes a lot of sense that I talk today about visual localization within this tutorial. So within Niantic, so if you think about how to create an AR experience, you need a wide array of technology. So you need to bring multiple players of an AR experience into a common space. So this is AR sharing. You need to understand the 3D world in terms of semantics if you want virtual characters to interact with the real world. And you need mapping. So you need to reconstruct the 3D world, and you need visual localization to position yourself within this 3D world and interact with this 3D world. And this is why we are here today. So in Niantic, we are very interested in this technology. Here we see a video of a map of a real space, and we are all knowledgeable in this area. So we recognize a sparse key point map here. So we are interested in the traditional methods, as well as the new school of methods, as Thorsten would call them. Here we see a dense meshing approach to building a map, which does not use LiDAR, but it uses depth estimation on the phone. And of course, we're also interested in semantically understanding the 3D world, so semantic segmentation, which we will see in a moment. So where's the sky, where are trees that characters can climb upon, for example. So all this is basically needed to create these AR experiences. And if you are interested in any of those, then work with us, because we are hiring. We are always looking for good people. And if you think, well, maybe you're doing your PhD, you're not sure yet, there's also the opportunity to do an internship at Niantic. So we have a very successful internship program that runs now for 3 years, I think, and the outcome is very nice. So we had an amazing set of interns so far with very nice paper outcomes. And we will also have an internship program in 2022, and more information will be shared in November. So consider applying if you want to do an internship with us. We are nice people. Come work with us. All right. So this part of the talk is called Learning-Based Visual Localization. And actually, I think it's not a really good title anymore. This title traces back to early versions of this tutorial from 2018, 2019, where this distinction between traditional methods and learning-based methods, it made more sense. But today we are in a position where, okay, you have handcrafted relocalization systems like Active Search, which rely on SIFT, for example. But more and more we see even the traditional approach of local features and feature matching, they use learning-based features like D2Net, we have R2D2, we have HLog and SuperBlue and so on. So almost all visual localization systems now are in some sense learning-based. So what will I talk about in this section of the tutorial? I will not talk about the traditional sparse feature matching approach to visual localization with learned features. I will talk about methods that go further with learning, which try to learn other parts of the visual localization problem. Things like the total conversion of localization into a CNN, like PostNet does, like we transforming the whole problem into just one CNN, which solves it in a forward pass. This is one thing we will talk about, but also hybrid solutions, which we model feature detection and feature matching and so on with learning-based methods, but then do post-optimization like the traditional methods. So in this space, this part of the tutorial will be positioned. And I think it makes a lot of sense to look at the different stages in visual localization when we talk about learning, because sometimes when you say you train a visual localizer on something for something, this is a bit confusing sometimes because there can be different stages of training. And in this tutorial, I will use this taxonomy here, like 3 different stages of visual localization, and you can basically learn at different stages of this pipeline. So we have the preparation stage, which is basically scene agnostic. You have a lot of data maybe, and you can learn global descriptors, you can learn local descriptors. It's just knowledge about the world that you can extract from large scale data. And this data is not specific to the scene that you want to relocalize. Then you have the mapping stage, where you now have data of the specific scene where you want to relocalize. So you have training images of this specific scene, and you can use it to do a map of the scene, like a 3D reconstruction of the scene. And then comes the relocalization stage, where you use this map and you look for the position of the camera according to query images that you want to relocalize. And these stages are not specific to learning, actually. So if we look at a traditional method like active search that Thorsten invented, it also has these stages. So in the preparation stage, what active search does is build a visual vocabulary of SIF descriptors for fast matching later. So it builds a descriptor dictionary by quantizing the descriptor space. This is done offline. It doesn't really matter how expensive it is, because you do it just once, you do it on a lot of data. And then comes the mapping stage, and active search would triangulate the scene. So it would run call map, for example, to create a sparse SFM reconstruction of the scene using SIFT or whatever descriptor you like. And then comes the relocalization stage, where you do a discrete feature matching between the query image and the SFM reconstruction, and you do post-optimization. Another example here is HLog of Saline, which would, in the preparation stage, train all its components. So it might use Superpoint, it might use Superglue, it might use NetFlat for image lookup, and it will train all these things on a held out set of large data. And then during the mapping stage, it will create a retrieval index for fast image lookup, and it will also triangulate the scene using CoMap or whatever reconstruction tool. And then in the relocalization stage, it will do a nearest neighbor lookup and retrieve closed database images, and then do discrete feature matching on top of that to relocalize. So these are the stages that I will come back to again and again in this talk. And now, finally, to the agenda. What do I want to cover in this talk? I want to talk about absolute post-regression, and I will name this part the challenge. I will talk about relative post-regression, and I will name that part the promise. And I will talk about scene coordinate regression, and I will name that part the compromise. So what's it all about? What is the challenge? What's the promise? What's the compromise? I hope I can explain during my talk. So let's dive into absolute post-regression. So first, we want to explain what absolute post-regression is. Then I will talk a bit about what components can be used in these type of methods. Then what do we achieve with these methods today? And what is actually the challenge that I hinted at during the agenda slide? Okay, so going back to the stages, what does absolute post-regression do? And we will look at the example of PostNet, which was the very first absolute post-regression method that was proposed in, it's not the first one here. It was proposed in ICCV 15, I think. So the reference here is a follow-up work, but it's still called PostNet, this one as well. So PostNet, in the preparation stage, it would train a backbone architecture. Well, I think the original one used GoogleNet, and it was trained on ImageNet. So it was trained for image classification. That's why the last neurons here, they are painted in gray, because this is not actually what you want to use, the classification head. The classification head will be thrown away later. It's just for learning features on a large set of data for some auxiliary task. Then during the mapping stage, you take that network that you trained, you substitute the head, so you throw away the classification head and you add a regression head that has the post output at the end. And then you train it with the scene-specific data that you have. So you just treat it as a supervised learning problem. You have input images and you know the pose that is supposed to come out of it. And then you train it end-to-end with some loss that you want. And then during the relocalization stage, during the evaluation, you just put in your query image, and within one forward pass, you get the output, which is the pose of the query, hopefully. So very simple. what are the things that we can use to build such a system? What is the toolbox that we have available? And if you hope that I talk about architecture, building blocks, and attention and so on, I will not, sorry. I will talk about other things, which I think are maybe even more important, because if you screw them up, then your method is basically doomed from the start, or you will have a very hard time to compete with other methods. And I think one thing that is really important is the pose parameterization. So how do you represent the camera pose at the output of your network? What does your network actually predict? What are the output neurons representing that you have in your network architecture? We want to regress a camera pose. The camera pose lives in SE3, the special Euclidean group. It consists of a rotation, which is itself a part of SO3, and a translation. So you can represent a camera pose as a 4x4 matrix, for example. The translation part is more or less simple. So basically all methods just request 3 numbers, which are the 3 dimensions of the translation vector. But the rotation is more interesting and more important what you do here. You have different options how to represent a rotation. One straightforward one is to just predict the full rotation matrix. So for the rotation output, then your network would have 9 outputs. Of course, 9 numbers do not necessarily represent a rotation, so you have to somehow enforce the constraints of a valid rotation, that they are orthonormal and that the determinant is 1. There are other options. Very popular is a unit quaternion, so 4 numbers, which with the constraint that the length of these entities is 1. This also each unit quaternion represents a rotation. And there is also a minimal representation, minimal in the sense that the rotation in 3D has 3 degrees of freedom, and you can represent it with 3 numbers. That's minimal. And one of these minimal representations is the axis angle representation. You have the rotation angle. This is a normalized vector. But then this normalized vector is multiplied with a scalar such that the length of the vector represents the angle of the rotation around that direction axis. And the axis angle representation is related to the rotation matrix via the logarithmic map. So if you read that somewhere, this is just how you go from a rotation matrix to the axis angle representation. This logarithmic map in 3D can be calculated in closed form, and that's called the Rodriguez formula. And this basically tells you how to go from a rotation matrix to the axis angle representation. There's also a log unit quaternion representation, which you sometimes encounter in the literature. This is basically the logarithmic map applied to quaternion. And this is equivalent to 2 times the axis angle representation. So this can be a bit nasty, because if you have libraries that do a transformation from a rotation matrix to an axis angle representation, these will map 9 numbers to 3 numbers. But if you misinterpret these 3 numbers, if you confuse axis angle and log unit quaternion, which are very similar and both are represented in by 3 numbers, then you get this error scale of 2. You have an error scale factor of 2 between those. So be careful when you use these concepts to not mix them up. All right, so what should you use? There are different options here on the slide. 2 years ago, when I presented this slide in the last tutorial at ICCV 19, I was basically describing this slide from front to back, and I would say, well, I mean, it's obvious that you do not use the rotation matrix. No one predicts the full rotation matrix with a neural network. That's just stupid. But it turns out that's actually people use this, And actually, this works very well. And probably this is actually what you should do. So forget what I said 2 years ago. Actually, you should predict the rotation matrix. And you can do this in different ways. You can predict 6 numbers, which you interpret as 2 vectors in the orthonormal basis of the rotation. And you do a orthonormalization of these 2 vectors to get a full orthonormal basis, for example, by using the Gram-Schmidt process to go from 60 to 90 and ensure the orthonormal constraint. Or you can also predict 9 numbers and then do an orthonormalization by orthogonal procrusts. And this, both of them have been used in papers, and both yield very similar and very good results. So one of these papers actually has this plot, and I love this plot because it tells you that different representations work differently well for neural networks, and there is a hidden gem, I would say, in this plot. So there are so what we see here is an experiment where you train an MLP to map the rotation matrix to the representation that you want. So you take 9 numbers of rotation matrix, you have an MLP, and it maps this rotation matrix to a representation, and this experiment to one of the representations that we see here on the plot. And this basically is supposed to tell you how good these representations can be learned by a neural network. And we see some of the ones that we had on the previous slide, the 6D and the 5D representations are basically predicting 2 vectors and then doing orthonormalization. Then we have 2 flavors of quaternion prediction. We have axis angle and we have Euler vectors. Euler vectors don't work very well because they have problems like gimbal lock and so on. So that's very confusing. We have quaternions that work much better than the Euler vectors. And we have also the 60 representations, so basically predicting the full rotation matrix, which works very well. So what is the hidden gem in this plot, which I refer to? I think this one, because there are two things here. There's the axis angle representation, which we have seen on the previous slide. And there's something like called the Rodriguez vector. And I was very confused when I saw this because the Rodriguez vector is probably you take a rotation matrix, you apply the Rodriguez formula, and then you get a 3D vector. But this is actually the axis angle representation. So these 2 should be the same. Axis angle and Rodriguez vector, that should be the same. But in the plot, we see a huge difference. So the axis angle representation actually works much better than the Rodriguez vector. So what's happening? Do I misinterpret the plot, or what's up? So I contacted the authors, and they said to me it's a difference in implementation. So axis angle here means that the network predicts a normalized direction vector and additionally the rotation angle. So it does not predict 3 numbers, but 4. Whereas the Rodriguez vector is actually the minimal representation where you multiply the 2. You take the normalized vector and you multiply the 4th number, the rotation angle. And this alone makes a huge difference. It's much easier for the neural network to separate these 2 entities, the direction and the angle, and predict them separately, than to basically mix them together. And it's very surprising, right? So, and this basically reinforces the notion that you have to try out, unfortunately. So deep learning so far has been an empirical science. You can go back to the theory to come up with ideas, but basically you have to go to the experimental stage and then verify and try around. And the takeaway from this plot is that it matters. So it matters what you use as the output representation, and you should probably use the 60 or 90 representation that predicts the full rotation matrix over the minimal representations like the axis angle representation, which are arguably more elegant, right? But the others work better. All right, so now we have decided on representation, but how do we define the loss? So we have a ground truth camera pose and a predicted camera pose. How do we compare the two? Where the translation part again is easy. You can just compare the Euclidean distance of the predicted translation and the ground truth translation. But how do you measure rotation error? So I think there's a very intuitive way of measuring rotation error, and this is actually the angular distance. So you could take the two rotations that you have, and you just calculate the angle between the two. And it does not matter which representation you use, because the mappings of representations across each other, they are differentiable. So you can always calculate the angle of the angle difference between the rotations and minimize this if you want. And because this makes sense, because usually in the evaluation, when you calculate errors on the test set, this is what you measure. You measure the angular error. So I would say you should also minimize the angular error as a loss. But there have been other things used in the literature. So for example, if you parameterize your rotation by quaternions, you can also use the Euclidean distance on the quaternions themselves. And this is a valid loss. So if you have two quaternions, like here on the right-hand side, the rotation angle, the angular distance, is the geodesic distance on the unit sphere between these two quaternions. If you measure the Euclidean distance, then you basically take a shortcut. You do not measure the geodesic distance, but you measure the Euclidean distance, which is an underestimate basically of the true angle if your quaternions are far apart. But this is, it's not too bad. You can see it as a robust loss function, which basically suppresses large errors, and this can work well in practice. What's also used in the literature is the Euclidean distance on axis angles or log quaternions, so these minimal representations. And this actually is, I would not advise this if you do this. It has been used and it has successfully been used, but in theory, this loss is not B invariant. That means that it depends on the global orientation of the two rotations that you compare, what loss you get. If you have two rotations and you change the global orientation of them without changing the relative angle between them, this Euclidean distance between the two will vary. So this, in theory, this loss is not well behaved. So I would just not use it. There's no reason to use it. Good. There's one more possibility, or one more aspect that we have to look at. So we have looked at rotation error, we have looked at translation error, but of course we want to minimize both. So we have to do some weighting of the two. And of course you can insert an arbitrary weighting factor that you hand tune. But there's also a formulation introduced by Kental and Cipolla, which say, okay, you can also make this weighting. You can learn this weighting. So you have two parameters here, ST and SR. And these are learnable parameters, which can be minimized by the optimization that you solve during learning. And the gist here is that you use the exponential of minus ST, for example, as a weight for the loss term. So if this weight rises, if this weight is increased, then the loss term will be down-weighted, but you pay a penalty for this. So you add ST as a penalty. So if this increases, then you also pay a large penalty. You do the same for the rotation loss, and then these two balance each other out. And Kental and Cipolla showed that this it yields a good trade-off between the two loss terms. And there's another possibility, which I think is also quite elegant. You can measure the reprojection error between the predicted pose and the ground truth pose if you have a 3D model of the scene. So H in these slides here, it will always mean the camera pose. H star is the camera pose. And we assume here we have a 3D model with vertices V. So we can project them into the image with the estimated pose. We can project them into the image with the ground truth pose. And then in image space, we can measure the error between the two. And this is nice because the localization problem gets more difficult the further away the scene is. So if the scene is very far away, then a 1 meter error actually is not so bad, because you would not even see a difference in the reprojection of the 3D model of the scene. Whereas if the scene is very close, like 1 meter away, for example, the position error of 1 meter, the same position error of 1 meter is very bad. And the reprojection error basically takes care of this. It marginalizes the distance to the scene out, so to say. So this is quite elegant, but it needs the 3D model of the scene to calculate this. Okay, so we have talked about the toolbox. We have seen some components that we can use in absolute post-regression. So now it's time to look at the results. What do absolute post-regression methods achieve today? And I have a little plot here that I will fill. And on the x-axis, we see the progress since 2015. And on the y-axis, we see the median error, the average median error that these methods do on an indoor data set like the one we see on the right. So we start first, let's establish some baselines. So we have active search, feature-based methods by Thorsten, which was proposed in 2012 and is somewhat a traditional SIF-based baseline. And this baseline would achieve a median error of around 5 centimeters on an indoor scene like this. And we have also a state-of-the-art learning-based method, a DSEC star, which is also a structure-based method. So it works similarly to active search in a sense. And we will learn about DSEC star later in the talk. And this is what we can achieve on this data set today, a median error of around 3 centimeters. Okay, now let's see what absolute post-regression methods do here. We start in 2015 with the original PostNet, the very first one, which achieved a median error of 45 centimeters. So quite large, actually. Then 2 years later, we had spatial LSTM, which decreased the error a lot to 31 centimeters, so we're getting closer. Then there was PostNet Plus, I call it here, also from Alex Kendall, which achieved 23 centimeters. So we are on a nice trajectory down. Then in 2018, we had MapNet Plus, or we had the MapNet paper. And this variant here, which achieves 18 centimeters, actually does a lot to get there. It adds better pose losses. It adds multiple query frames to the estimation, and it adds post-graph optimization on top of that. All this to squeeze out 18 centimeters median error. Then in 2020, so there are more methods, of course, right? But my little zoo here would continue with AdLog in 2020, which used attention in the absolute post-regression architecture to achieve 20 centimeters median error. Then we have GLNet also in 2020, which used GNNs, graph neural networks, on the query side. It uses multiple query images and a GNN on top to achieve 19 centimeters median error on this data set. And this year at ICCV, we have the MS transformer method, which achieves 18 centimeters by combining basically multiple scenes into one architecture. Okay, so we have to say, we see basically that we are still somewhat off what traditional methods can achieve. So absolute post-regression does not yet achieve what structure-based methods like active search and DSEC can achieve. And we also see that since 2 or 3 years, progress is stagnating. We are basically meandering around the 20 centimeters median error, and there was no big breakthrough since for absolute post-regression methods. But there has to be something. There has to be a wall that we are running against. So what is the wall? What's going on? Why can these methods not perform better than this? So here on the slide, I compare. We have the results of the original PostNet. We compare it to the median error of active search and DSEC-star, like in the previous slide. And PostNet and DSEC-star, they are learning-based methods, and active search is a traditional SIF-based method. And we can compare that to a traditional method, DenseFlat, which is a retrieval method. And the sense here of this graph is to show where DenseFlat and PostNet actually have very similar median errors, very large median errors and very similar median errors. And they are both global methods. So they look at the whole image and they try to, the DenseFlat would match it to the closest database image and take that pose. And PostNet would do something similar, but within the neural network, right? It has been trained on all the database images. Then it looks at the global image and predicts the pose, which is very likely to be close to the database images that it has seen during training. And this has actually been shown in a paper by Thorsten, Understanding the Limitations of CNN-based absolute post-regression in CVPR 19. And the reasoning here is the following. So we have an input image. We have the absolute post-regression network, which predicts the output pose. And this absolute post-regression network consists of n layers. And if we look at the last layer, it would look something like this. So we have the output pose, which are 7 numbers. Then we have in the layer before, we have an activation vector or global feature, which has 2000 something dimensions. And between the two, we have the last weight matrix, which is applied. This weight matrix is a linear projection of the activation vector of this global feature to the output pose. And you can interpret this weight matrix as a base pose, as base poses. And in theory, you just need 7 base poses to represent the whole pose space. But in practice, you can imagine that from a limited number of database images, absolute post-regression network will have a hard time of learning a set of base poses, which when you interpolate them with the activation vector, gives you the right output pose. And this is actually what Thorsten shows in this nice set of experiments. Here we see an image where we see a training trajectory in red, a test trajectory in green, and then the output of PostNet and MapNet given the green query images. And you see that they fall back to the training trajectory. So they can only interpolate between the database image poses that they have seen during training, and they have no means to escape that. Whereas methods like active search, structure-based methods here seen in Cyan, they can, from the same training data input, can infer the test poses. Okay. So there's another thing which I want to, another aspect which I want to highlight here. So assume we have a training image and one training image, just one, and you train a absolute post-regression network to predict the one ground truth pose that you have. So your training database consists only of one image. You overfit your network to this one image to predict the one output pose. Now you have 2 test images. One is just a translation of the training image to the left, and the other one is just a rotation. So a absolute post-regression method has no way to know how the camera pose should change in these settings. It has only seen one view. The global image, of course, completely changes when you when you go to the left or to the right. So the absolute post-regression method will necessarily fail because it has to extrapolate and cannot from the limited training data that it has. Local methods like active search, feature-based methods, and also DSEC**, which we will see later, they have a very different task. They need to learn to be invariant. So if you look at the chess piece and the small patch around it, when the image is just translated, it's just a matching problem. Actually, the patch itself, it has not changed. It's just at a different position. You just have to find it. And even if the image rotates, then the patch changes a little bit, but locally it doesn't change so much. So if your local descriptor learns to be invariant to these changes, then you can still match it, and then your relocalizer still works. So to wrap up the absolute post-regression part, they have a few advantages. They are actually very fast because you compute the post in just one forward pass, but so far they have low accuracy, and it's unclear whether for a specific scene you will, in any case, have sufficient training data to learn these methods. There is some indication that more training data helps. So in the limitations paper from Thorsten, he has a synthetic experiment where he synthesizes in a synthetic rendering of a scene more and more training data, and you indeed see that the absolute post-regression methods get better. So synthesizing training data might be a way out, but in this experiment, even if you for a very small scene synthesize almost 10,000 images, it still is far off a structure-based method, which in this case is active search. So maybe this is a way out, but it's not easy. Okay, let's come to the second part, relative post-regression, which I call the promise. And we will see what is relative post-regression, what can they achieve, and what is the traditional baseline. So we go back to our post-estimation stages, and we will look at the ReLocNet example. In the preparation stage, you do two things. First, you pre-train a global image descriptor to do image retrieval. This is one part of these methods. And then you also train a relative post-regressor on this data, which takes two images, a query image and a nearest neighbor database image, and is able to regress the relative post between them. And these two components can be pre-trained on different data, on a large data set, which is not scene data, pre-trained on this data. And then during the mapping stage, you build your image retrieval index. And when you then have your query image during test time, you look for the closest database image using your image retrieval component. And then you use your relative post regressor to basically refine the pose of the closest database image by relative post regression. And this gives you, if you combine the absolute post that you know of the closest database image with the relative post to the query image, this gives you the absolute post of your query image. And the promise here is that the mapping is very cheap. You do not have to train on scene-specific data. You just build a retrieval index. All the training happened before. It happened on unrelated data. And then you can just apply your trained components, build an index in mapping, which is very fast and very scalable. And then during relocalization, you just apply your pre-trained post regressor to get the absolute pose of the query image. So this is the promise of this. Where do we stand? So this is a huge table. I will walk you through it step by step. This is from a recent 3DB paper of Turkoglu, where I was also involved. And here we compare different families of methods. So first, here on the top, we have the state-of-the-art structure-based methods on this data set. And then we have the family of methods, which are absolute post-regression methods, which learn scene-specific representations, like in the first part of the tutorial. And the first four of them, they are sequence-based, so they would use multiple query images. And as I have said a few moments ago, it's reasonable to compare them to image retrieval methods to see whether they can, whether they actually do something reasonable compared to very naive image retrieval based baselines. And in many cases, we see that a dense flat classical image retrieval approach is more accurate than many of these absolute post-regression methods. The relative post-regression methods, they should at least be more accurate than the retrieval methods because they build on top of it, right? They start with retrieval and then they refine basically using relative post-estimation. So they should be better than these retrieval-based methods, and they are. So if you look at the last column, then most of them are better than the retrieval-based methods. And we see in the bottom of the table, we see ChemNet, for example, which achieves excellent scores of 5 centimeters median error on this data set, which is very close to what DSEC-STAR does actually on this data set. But we have to say, so in our work, which is cited here on the bottom, we try to build on top of these works actually. And we used the public code, and we were not able to replicate these results. So these methods, ChemNet and also Anchor Point, which has also very good scores. These methods have code online, but we were not able to reproduce the results with the public code. That doesn't mean that these numbers are not valid. They are published, and we have to assume that they are valid. It just means that the code, which is online, does not produce these numbers, which is, of course, a big problem because people look at the code assuming that it would produce these numbers and then waste time, basically, to get it working, but it doesn't work. So this is a bit of a problem here. Okay, there's another big caveat here with these relative post-regression methods, because they have all been trained on the very same data set. So all these methods here in green, they follow the relative post-regression formula, but they cannot fulfill the promise of relative post-regression yet, because they were all trained on scene-specific data. And in the work of Su in ICRA 20, the authors have shown that relative post-regression methods actually do not generalize very well. So here we see that if these methods are trained on a Cambridge data set, which is an outdoor data set, and tested on an indoor data set, then the scores are much worse than as if you would train on the same indoor data set. I think these numbers are a bit exaggerating things, because it's if you train something only on outdoors and then expect it to work indoors, that's quite extreme gap to generalize to. But the point still holds, because ReLocNet, for example, has an experiment where they trained on a separate data set, ScanNet, which is also an indoor data set. And they report lower accuracy than if they would train on the actual data set that they test on. So if you train on different data sets, then your accuracy deteriorates. And in this case, in the case of ReLocNet, it's one of the few methods that does this. It works not as good as the dense flat baseline. Another aspect here is that the claim of relative post-estimation methods is that they come without mapping cost. All the methods that we have seen before, active search, DSEC-STAR, absolute post-regression, they have to train or reconstruct on scene-specific data, which takes a long time. And relative post-regression methods claim they do not need to do this. But you can achieve the same with a traditional baseline. What could a traditional baseline look like? This is also from this ICRA paper of Su, where they show that with SIFT and a 5-point algorithm, you can have the same properties, namely without creating an expensive 3D reconstruction of the scene, you can still estimate the pose. In the preparation stage, you do nothing. Then in the mapping stage, you build your retrieval index using a classical approach like dense flat. Then in the evaluation, you get your query image, and you do feature matching between the closest database image and the query image, and you estimate the essential metrics. The essential metrics can be decomposed into the rotation and the translation, but only up to scale. So you get a relative pose, but you don't know how far the query image is away. The translation vector is unscaled or has a unit scale. But the way around it is to just do the same for a few more database images, estimate the relative pose as well, which are also unscaled. But then you can basically triangulate the translation vectors to get the absolute precision, the scaled absolute precision of the query pose. And this is a traditional baseline, which has a very cheap mapping stage. It just needs to build a retrieval index and can give you a absolute pose, a scaled absolute pose of the query image. And this baseline achieves a median translation error of 8 centimeters in this data set here. So it's twice as accurate as our method, which we published in 3DV, which is the best reproducible method in this table here. So in essence, we have to say that the promise in visual relocalization has not been fulfilled yet. So most of the relative post-regression methods, they are still trained on map-specific data, and they are worse than a traditional, they do perform worse than a traditional baseline. There is, however, some indication that depending on the structure of your data set, these methods can outperform classical baselines. So this is from a CVPR paper from 2021 from Chen and colleagues. And here, this is evaluated not in visual relocalization, but just the relative pose estimation part. And we see here some indication that for white baseline stereo, so when there's very little overlap between the two images, then a learned approach can indeed outperform SIFT and RANSAC as a baseline. The other side, of course, is that we have better methods now than SIFT and RANSAC. So if you would use SuperBlue and SuperPoint, would it still hold what they show here on the slide? I don't know. But it is an indication that there is a hope for a relative post-regression methods if your data set is structured in a way that it's unfortunate for the SIFT baseline. So to wrap up the relative post-regression part, it works at least better than absolute post-regression. The promise is that you virtually have no mapping costs. All your training is done offline. It doesn't matter actually. So it's cheap. But the generalization has not been shown so far, or so far it has been shown to be poor. So the promise has not been fulfilled yet. Okay, so we have seen two methods which do not work yet, as much as we know at the moment. And I will close the talk with a method which, at least in some scenarios, actually works. And that's why it's called the compromise. It's a mixture of traditional methods and learning-based methods, and it works quite well. So we will define what sync-coordinate regression is. We will look at how random forests solve this, how CNN solved this, and we will close with some remarks on benchmarking. So here is a summary of feature-based matching. So we have an image, we do feature extraction and feature matching. There might be some wrong matches, but we use RANSAC, PNP, and we count inlies and so on within RANSAC to estimate the pose. This is on a very crude approximation what active search, for example, does. Now, the idea of synchronous regression is that you throw away the feature detection and feature matching and substitute this with a learned function. The learned function takes an image patch as input, and it directly predicts the 3D coordinate in scene space. So this would be normally the output of your matching, right? And if you do this for all the patches of the input image, you get a dense correspondence field, which we will visualize here by mapping the 3D coordinates of the scene to the RGB cube. So this colored image here represents a dense matching to the scenes. And the first methods that proposed this, they were using random forests to represent this function, which takes an image patch and maps it to a 3D coordinate. These random forests, they would, during training, take all the patches of your training images. They would build a tree from that by looking at pixel differences within the patch as features. Then they would split the patches by reducing the spatial variance of the 3D coordinates that belong to them. And then in the leaf nodes, you would fit a distribution about the 3D coordinates that you have in the respective leaf. And if you then do the prediction, so if you apply the trained random forest to a query image, you get something like this. So on the left, we see this noisy prediction of the random forest. On the bottom right, we see what the ground truth looks like, and we see that it mostly makes sense. It's maybe a bit noisy, but actually it works quite well. And the early methods there were using RGBD to train these forests. And also during test time, they were relying on RGBD queries. And they were working quite well. So at the time, so we see here in the table, we see RGB methods on the top and RGBD methods on the bottom. We have active search and HLOG as baselines. HLOG didn't exist yet when these methods were proposed. So it's interesting to see the relation now. And these RGBD forest-based coordinate regression methods, they can improve upon these baselines, basically. We also have a scene-coordinate regression forest-based method which works on RGB, which I proposed in 2016, but this does not hold up so good anymore. So with 55.2%, it's not competitive anymore. But you can do it in RGBD and RGB. And then the nice thing about random forests is that you can actually train them offline as well, and then adapt them on the fly during mapping, making this even faster during the mapping stage. So the idea here of on-the-fly adaptation is that in a preparation stage, you train your forest structure on an unrelated scene, something else, some indoor data set. And then you keep only the structure. You throw away whatever you learned in the leaves. You only keep the structure. And now if you go to a new scene that you want to map, you basically pour in, as you go, patches from the data that you observe. And because you have depth and the estimated pose from the previous frame, you do tracking as you go, you can update the feature distributions in the leaves to get a scene-coordinate distribution in the leaves on the fly. Basically, fill the leaves as you go through the scene. And then if you want to relocalize, if you lose tracking and you say, okay, now I want to relocalize, then you go to evaluation mode and then you look up the leaf distributions and can use it as original scene-coordinate regression. And these methods perform excellent in these indoor benchmarks that we have. So these actually outperform the non-on-the-fly methods that we have seen before. So this is very nice. The authors also proposed this for, in the follow-up paper, how to do the same with neural networks, not with random forests. So check that out if you're interested in this, but it wouldn't work as well as with the random forests, interestingly. Okay, so to wrap up the random forest part, they are very fast, both in training and inference. They can handle ambiguities because you have distributions in the leaves, and they have very solid accuracy. This advantage is that they need a 3D model for training. So you need depth during the training stage, which you either get by a sensor or by rendering a 3D model of the scene. Now, a newer kind of work for scene-coordinate regression substitutes the random forest for a neural network. And you can, of course, do this. The neural network takes an image patch, so you don't change the formula. This is now a neural network that predicts the 3D coordinate for an image patch, and you get a nice, smooth prediction like this here compared to the noisy forest prediction. Problem is that not necessarily the smooth prediction works very well in practice. Can be that actually the CNN-based prediction leads to a bad pose estimate compared to what the forest predicted. Because it depends what loss function you use for the neural network. So when you use the L2 distance between the ground truth scene coordinates and the predicted scene coordinates, you will get an error histogram of your scene coordinates like this. The green one is the previous random forest, the orange one is the CNN, and we see that while the CNN does actually a pretty good job, it has many inliers within the inlier threshold, but the accuracy peak of the inliers is worse than the random forest. So, and because we have RANSAC, which basically picks the best inliers, the random forest often performs better than the neural network. But this can easily be fixed by fixing the error function that the CNN uses. If you optimize an L1 loss, then the CNN does actually much better than the random forest. So choose your error function wisely. You can even switch to a reprojection error loss if you do pose estimation from RGB images. So here on the left, we see the formulation. The gist of this is you optimize the distance to the ground truth scene coordinate, the one distance, up to a certain threshold, and then you switch to the reprojection error. You minimize the reprojection error of the scene coordinate that you predict using the ground truth pose. And this works very well both in RGB with the reprojection loss or with the L1 loss if you do RGB estimation, as we see on the right. The reprojection loss has another very nice property, because if you look at the formulation of the reprojection loss, it only depends on the ground truth pose. It doesn't need the ground truth scene coordinates anymore. The ground truth scene coordinates are actually only needed for the initialization part, and you can reformulate the reprojection loss to substitute the ground truth scene coordinates with a heuristic. You just say, okay, I do not know the ground truth scene coordinates. I just assume there's a constant distance to the camera plane, and you plug this into this formulation, and this actually still works very well. So you optimize the heuristic, and then when the heuristic is satisfied, you switch to the reprojection loss, and then the network will discover the geometry of the scene by itself. You don't need ground truth anymore. This means you can just train with RGB images and ground truth poses. You don't need depth, and you don't need a 3D model of the scene. This works quite well. You lose a little bit of accuracy, like 5% on this data set here, but you gain that you can handle data which hasn't been recorded with Kinect, for example, which is very nice. There are also works listed here from Lee et al., which use multi-view constraints to improve learning without the 3D model, and according to their baseline, this works as well. But in absolute terms, there's still a gap to recent methods like DSEC-star. But there are different. These are not directly comparable because these are different methods. So multi-view constraints could help maybe. Geometric losses and photometric losses can help, but we don't need them to achieve high accuracy. And actually, it's surprising that you can optimize the reprojection error and discover the geometry of the scene, right? Because the reprojection error is ill-constrained. The true geometry can, if you just minimize the reprojection error, it can lie anywhere on a ray to the scene. But during the training of the network, it sees the images from different directions, and it implicitly can triangulate the correct depth of the geometry. And you can train, or you can extract the 3D models that the network learns and look at them. And here we see a few models that I created. So in the top, we see the ground truth 3D models that have been recorded with Kinect. If you train the network with RGBD inputs, then you see a very nice reconstruction. So it basically learns this 3D model that it was trained with, unsurprisingly. If you use a 3D model, if you use rendered depth for training and not a true depth, then you get almost the same. And if you use the RGBD formulation, if you just optimize the reprojection error, you get also very nice reconstructions which has some holes. As you see, this is where the implicit triangulation does not work. But overall, it's still enough to get very nice relocalization rates. But there's still one thing that we would like here. So far, we have only seen losses which are defined between the predicted sync coordinates and the ground truth sync coordinates. But then there's this whole process afterwards, RANSAC, PNP, inlier counting, and then you only get the optimal pose at the very end. And actually, it would be nice to define a loss on the predicted pose and minimize this loss, minimize the loss between the estimated camera pose and the ground truth camera pose. Is this possible? Well, yeah, it is actually. So let's walk through the pipeline. We start with an RGB image. Then we have our sync coordinate regression network, which predicts sync coordinates. We do RANSAC, so we sample different pose hypotheses by sampling minimal sets. If we want to do end-to-end learning, we have to differentiate PNP, our minimal solver. This is possible. You can look at the reference at the bottom how to do this. You basically you interpret this as a iterative optimization problem, and then you can propagate gradients through the iteration to differentiate PNP. Then you calculate for each hypothesis, you calculate reprojection errors, you count inliers as you would in normal RANSAC. The inlier counting can easily be made differentiable by just using a sigmoid function instead of a step function. The soft inlier count is differentiable. And then at the very end in RANSAC, you do a argmax selection, right? You select the hypothesis with the largest inlier count. This is what RANSAC does. This, unfortunately, is not differentiable. So what do we do here? So we have to have a way to reformulate this argmax selection to make it differentiable, to make it soft in a way. And one way to do this, which we propose in the differentiable RANSAC paper, DSAC, is a probabilistic selection. So you select one hypothesis randomly, you sample the hypothesis according to the scores that it achieved. A high score, a high inlier count means a high probability to be selected, and a low inlier count means a low probability to be selected. So you make a probabilistic action out of your hypothesis selection. And then the DSAC learning objective, which you can use for training, is you minimize the expected loss that you get. So you sample one hypothesis according to the inlier count, then you minimize the expectation of the loss that you get when you sample. And you can imagine that if you minimize the expectation, what does the network do? If you have a bad hypothesis with a high loss, then it has to minimize the probability that this loss is selected. So the inliers have to go down, the inlier count. The bad hypothesis is not allowed to have a high inlier count. On the other hand, if you have a good hypothesis with a low loss, then you want to increase the probability of that. And that means that this pose should have a high inlier count. And the network will adapt its predictions to guarantee these conditions. And then if you train the whole pipeline end-to-end with this DSAC objective, you get a nice boost in accuracy. So for RGB methods, it's plus 5%, and for RGBD methods, plus 3%, and we are performing quite well with respect to the competition. And here we see a qualitative example of what end-to-end training does. So end-to-end training basically focuses on different parts of the scene. So whatever is blue here is the reprojection error after end-to-end training improved. So it focused basically on these parts of the scene, and everything that is red was neglected. It was an outlier anyway, and it got even worse after end-to-end training. So end-to-end training leads to a focus on certain reliable parts of the scene. So some words to the inference speed of these methods of CNN-based sync-coordinate regression compared to other methods. So these are the query times per frame. And we see that active search is quite decent with 50 milliseconds. PostNet is very fast. Absolute post regression is very fast because it's just from one forward pass, a few milliseconds only. Random forest can be very fast, even on CPU. I think these 100 milliseconds here are on CPU. DSEC++, the previous methods before DSEC star, it used 200 milliseconds per query frame, and now with DSEC star we are at 75 milliseconds or 30 milliseconds. And what I really want to tell about this table is that all these numbers are not in the least comparable, because they were calculated on different hardware, and they are just not comparable, and you should not compare them in papers, although people do. And sometimes people say, well, the hardware it doesn't matter so much, but it does. So for DSEC star, I measured the time on 2 GPUs. On a Tesla K80, then it takes 75 milliseconds. Or on a GeForce GTX 2080, then it takes 30 milliseconds only. So it depends very much on the hardware. These methods can be fast if you have decent hardware, and they will be slow if you don't have decent hardware. So that's just how it is. So this method, it's very hard to do a fair runtime comparison. Same for training times. So active search has to be the SFM reconstruction, which I think can take a few hours. PostNet is trained within 1 hour. Random forests are trained within minutes. So they are very fast to train, and on-the-fly adaptation is virtually real time. DSEC++ had to be trained 6 days on a Tesla K80 GPU. DSEC star trains 2.5 days on a Tesla K8 CPU. GPU, but here again, if you switch the GPU to a GTX 2080, then you go from 2.5 days to 16 hours. So please be careful when you do runtime and training comparisons, time comparisons in your papers, because it's a mess. So it depends so much on hardware that there are no valid conclusions that we can draw here, up to certain bounds. So still, we can say that sync-coordinate regression with CNNs is very expensive to train, even if you 16 hours is still a lot, right? Random forests are much faster and have decent accuracy, and depending on how fast your SFM reconstruction is, traditional methods also take a bit of time, but maybe only on the CPU, so it's really hard to tell. Another aspect is how much memory do these methods need? So here we have a table, and I try to make it a bit more readable by coloring it. So we have a ranking here between the different methods and how much memory they use. On the top, we have active search, which needs memory for the SFM reconstruction that the tools was seen, where it does matching. Then we have a compression method, which disregards many of those 3D points and basically specifies the SFM reconstruction. We have retrieval-based methods and PostNet as an absolute regression method, which just has a quite small network of 50 megabyte. DSEC++ needed 200 or 100 megabyte. It actually depends on the learning framework that you use. And the recent DSEC star only uses 28 megabyte, and you can only also reduce the network size as you wish, right? You can downscale the network and then just use a reduced capacity and see where you land. And in this coloring here, we see actually that sync-coordinate regression, especially with the ResNet architecture of DSEC star, is a very good compromise between scene compression and accuracy. So with as little as 3.8 megabyte, which rivals hybrid compression and dense flood in memory footprint, you can get decent relocalization rates. So advantages of sync-coordinate regression with CNNs, high accuracy. You can train end-to-end. That means you are very free to define the loss that you want to optimize and then just go crazy with that. You can train with and without a 3D model of the scene, and you have very good scene compression. Disadvantages, it's very slow. You need a good GPU, especially for training. So training will take a few hours if you even with the recent methods. In relation to the random forest, there's an interesting work which shows that actually there's a mapping between random forest to CNNs, and there's a work that explores this for visual relocalization. So that's quite interesting, I think. One thing that is left open, so all the data sets that I've shown so far, they are all indoor data sets. So these scenes are quite small, they are room size. So how does sync-coordinate regression with CNNs scale? So if you apply it to large outdoor data sets like Aachen, which is 2 orders of magnitude larger, then your accuracy just breaks. So here we have for DSEC++, we measured a accuracy of 0.4%. So it just doesn't work on this large outdoor data sets. And in the middle, so we tried, okay, what happens if we just stay indoor, but we combine different rooms into a larger environment? And we see already there, we see a decrease in accuracy for DSEC, for these sync-coordinate regression methods. What do you do if you have a large scene and you cannot scale? Well, the solution is quite easy, actually. You cut it into pieces until you have a small scale problem. So you cluster the large environment that you have, and you train a sync-coordinate regression network for each part. And then you have to have a gating network, which tells you for a query image which of the networks that you trained is responsible. And we did this in ICCV 19. It was called Export Sample Consensus, or ESAC. This was the basic idea, just cut it down into pieces. There's a bit of intelligence here. So it does not select networks based on the query image, but it distributes budget of RANSAC to different experts. And you can train everything jointly and end-to-end. So that's really nice. But the basic idea is take a big one, cut it into smaller ones, and make the large-scale localization problem a small-scale localization problem. And ESAC recovers some accuracy compared to DSEC++. So DSEC++ had 0.4% accuracy. ESAC has 42.6% accuracy. But if you look at the whole picture, so if you compare ESAC to feature-based methods on these large-scale data sets, if you look here to the very right of the plot, you see that it's still much less accurate than feature-based methods on large data sets like Aachen. ESAC reaches like 40% accuracy, whereas active search and other HLOC and so on, they reach more than 80% on this data set. And this is a pattern that we have recognized across data sets. So it seems that outdoor data sets, sync-coordinate regression does not work so well. And for indoor data sets, sync-coordinate regression outperforms traditional methods. This is what we see in these plots here. So for indoor data sets like 7 scenes, sync-coordinate regression, especially if it's based on RGBD inputs, it outperforms classical approaches like active search. For outdoor data sets, sync-coordinate regression does not reach the accuracy of feature-based methods. But actually, if you look closer at the results for ESAC, there's something weird here, I would say. Because so people say that sync-coordinate regression does not scale to big outdoor places. But for ESAC, we said, okay, we cut it down. We cut it, we make it actually a small scale localization problem. And you see that if ESAC uses 10 experts, so it cuts the large environment into 10 pieces, you get quite a big improvement compared to DSEC++, which only uses 1 network. If you go to 20 experts, so you cut into 20 pieces, you still get a reasonable gain, like 10%, going from 30 to 40. But if you then rise to 50 experts, so you cut it into 50 pieces, there's not much happening. You gain like 1 or 2%. And there is still a huge gap to the feature-based methods. So it's not very plausible that scalability is the reason here, because then you would expect that the more networks you use, you close the gap. And 50 experts is a lot that trains for days, and it has a gigabyte of, or 2 gigabytes of capacity for these networks. So capacity is not a problem. Training time cannot be the problem. So what's the gap? And actually in a paper of ICCV this year, we look at another aspect that has been overlooked so far for all these benchmarks. Namely, what was the algorithm that generated the ground truth for these data sets? Because there's another correlation here. It's not only outdoor versus indoor, but the correlation here is also for the indoor data sets. The ground truth has been calculated with RGBD SLAM, whereas for outdoor data sets, the ground truth has been calculated with SFM. Could that play a role maybe? So if you look at these two algorithms, then both of them, DSLAM and SFM, generate very good camera poses. So I don't know how well this video here streams to Zoom or to YouTube, but actually both methods are very good in calculating the trajectory of the camera poses. So it makes sense that people say, okay, this is good enough to use it as ground truth. But the two algorithms actually do not produce the same result. So there's clear differences between DSLAM and SFM. Yet some data sets use the one as ground truth and some data sets use the other as ground truth. So we compared actually what the difference is for the relocalizers by producing both versions of the ground truth for indoor data sets where we can use both algorithms and compare what algorithms do with that. So here we see active search on that use the DSLAM poses for mapping. And we see very high jitter and very low accuracy. But if we look at the same scene, we change nothing but the ground truth that active search uses for mapping, then suddenly active search works very well. Very low jitter, very low, very high accuracy. Before, people have said, well, traditional methods like SIF, they don't work indoors because there are just too many repetitions, there are textureless surfaces, that's why it doesn't work. But as you see, it works very well, actually, if you use the right ground truth. And right here means that not the true ground truth, because we do not have it, but a ground truth that fits the needs of active search, so to say. We can do the same for DSEC star. Here, the differences are not so pronounced. So DSEC star actually, with RGBD inputs, can use both versions of the ground truth reasonably well. The differences are not noticeable even, but they are measurable. So if you do the common metrics on benchmarks, then DSEC star performs better with the DSLAM ground truth than it would perform with the SFM ground truth. And we did this for 2 indoor benchmarks and for several methods. We compared the rankings that are in the literature, which are based on the DSLAM ground truth, and we generated alternative ground truth using SFM. And suddenly you see that the rankings completely invert. So suddenly active search that did not perform well before comes out on top, and DSEC RGBD suddenly does not work so well anymore. And this affects claims that have been made in the literature. So active search obviously works well indoor. Scene coordinate regression outperforms classical. Scene coordinate regression can outperform classical localization or not, depending on how you generate the ground truth. And RGBD methods can outperform RGB methods or not, depending on how you generate the ground truth. So all these claims from the literature, they are not wrong. We just have not sufficient evidence to support them. Because if you calculate your ground truth using SFM, then methods that are very similar to SFM will have an advantage and will come out on top. If you use DSLAM to generate your ground truth, then depth-based methods, which are very similar to the DSLAM methods, will come out on top. And in the paper, we show that neither of these two ground truths is preferable. They all have their own benefits and advantages. And it's not easy to say which one is closer to the true ground truth because we do not have it. This is a big problem, obviously, because how can we compare algorithms anymore? We propose some solutions in the paper, so check that out. But the fundamental problem does not change. It's still there. So this wraps up my part of the tutorial. We have looked at absolute post-regression. And the question here, and why it's a challenge, is there ever be enough training data to train absolute post-regression on a specific scene? We have talked about relative post-regression, but the promise that it makes, that it has a very cheap mapping costs, is not fulfilled yet because they cannot generalize very well from one data set to the other as this point. And we have talked about scene coordinate regression, which actually works quite well. So this takes basically the best of two worlds. It takes the domain knowledge that we have in traditional methods, but it substitutes the heuristics by learning that from data. And the big question mark in all of this is, how do we benchmark? So this is a big problem, maybe the biggest problem we have at the moment in visual relocalization. How can we do fair comparisons between different methods in benchmarking? Because we do not have the true ground truth, we only have estimates of the ground truth. And depending on how we generate it, some families have a benefit over other methods. And the comparisons that we do are not fair to an extent where some claims in the literature do not hold anymore. So what people believed is we have to go back a step and have to ask questions whether this actually is true. This concludes the tutorial. I think for many of us, it will also conclude the ICCV. I hope you had a great conference and great experience. I hope our talks were useful to you and you learned something. And I really hope that we see each other in person again in the next 1 or 2 years, when hopefully things go back to normal and we can meet in person again. Thank you very much.
And I don't think that there are any questions on YouTube. At least I don't see them. Yeah, I think we can conclude the tutorial with this. If people still have questions, they can post them on YouTube. We will probably see them, or send us emails. Yeah. Thank you very much for your attention.
Thank you very much, everyone.
Thank you very much.
Good. Yeah, thanks for setting this up. I think we can stop the stream now.